Hello, everyone. Let's test some sound.
Hello, Andrew. Can you hear me?
Yeah, hi.
Hi.
So, who out of you two will start presenting?
Hi. I'm Ty.
All right, I'll make you a presenter. Just a few minutes before 7. Let's wait for everyone to gather.
Cool. So, do I share my screen or how it work?
No, I'll make you a presenter and you'll get controls to switch slides and I'll pick your presentation. So,
All right. Okay.
it's all the power for me and you just
All right.
get controls
That's
when you get them. Yeah.
Cool.
But I'll give it a few more minutes to let others gather. We'll go through the standard, thanking sponsors, greeting everyone, and then we'll start the presentation at 7. And we'll try to stick to the schedule. So 40 minutes for the talk, 20 minutes for questions and breaks, and then next talk.
Do you think it will be possible?
Oh, actually, 10 minutes. Sorry. Sorry, what?
Yeah. All right. Will it be possible to control your file in the
Sorry, say it again.
Will it be possible to control to a file at the middle of the talk because we're kind of split between us? Sorry.
Yeah, just let me know and I'll switch who's presenter. If I understand correctly how all this works, we'll figure it out.
I'll start and then at the middle our file takes over and I'll just resume for the finish.
Okay.
How do you see me now? You had feedback that I'm a bit choppy.
You are for me, not sure for Andrew. Like when you talk, I can hear some splits.
All right. Is it the same for you, Andrew?
Sounds good on my side.
Okay.
Okay. All right. I'll stick with it.
Okay, so with 3 minutes to go, welcome everyone again. Happy morning to everyone on West Coast and good day for everyone else. Welcome to the last day of LPC conference, BPF Networking track. We'll go through 5 talks today, 40 minutes per talk, 10 minutes of break and Q&A in between. So please be conscious about the time. I have cards like this. If I will remember to show them, you will know when your time is coming up. And well, we'd like to thank our sponsors for making this conference possible. Thank you for Diamond sponsor Facebook, our Platinum sponsor IBM, Gold sponsors ARM and Microsoft, Silver sponsors AWS, Netflix, and Red Hat. Thank you to Collabora for speaker gifts, VMware for t-shirts, and of course Linux Foundation for just organizing this awesome conference so that we can all get together and talk about lots of technical stuff. Thank you to the planning committee, especially for coordinating all the important organizational moments. And with that, we'll be preparing for the next and first today presentation from Itai and Rafael called Towards Truly Portable eBPF. So let's give it another minute to start, like on 7 a.m. clock, and yeah, Itai will start. You should have gotten the controls, right?
Yeah, thanks.
Cool. Take it away.
All right. So, hi everyone. I'm Itai Shakuri, and with me today is Rafael. We're from the open source team at Aqua Security. Our team builds a variety of open source solutions for the cloud native secure space. One of the projects, Tracy, which is a runtime security tool that is using BPF, and we wanted to share our story of building and shipping Tracy, which is an eBPF application, and from our point of view, share maybe feedback and maybe there's for others in the same view as us. We're a vendor, we're not a user. We're building a process that is being used by others. We're not instrumenting our own class or trying to solve a problem for our own, which means that we don't necessarily have the same level of control that some of the others have. Maybe our users don't even have the same level of control because they are running in restricted or managed or compliant environment, and we have some challenges while building this. We're traditionally Go. All of our other tools are Go. We love Go. It helps us build quickly and ship it to any platform very easy. And Tracy is the first eBPF kind of product that we build, and we wanted to replicate this experience for the user experience of running this tool. Our philosophy generally is that we favor user experience, even if we need to work a little bit harder. And this is what we did in this case, and we will share our journey there. The end goal is to basically achieve something similar like Docker Tracy. This is like the end goal. Even for people who are not familiar with eBPF, doesn't have access to the operating system configuration, don't know kernel headers are, and so we still want to give them the same level of experience. All right, well, let's start by presenting where it's not where we're at, but it's a good place to start discussion. So we have this Docker image, Tracy. This is how we ship Tracy. It has the CLI binary, which is written in, this is the user space application, and we'll run this container. We'll compile the eBPF code. There's a lot of eBPF prog that we use, and it will compile on the target machine so that people can run this. It will compile eBPF prog, load it, and work. In order for this to work, we also needed to bundle into this container not just the source code, but all of the runtime dependencies, all of the tool chain, and so on. The external dependency that we have here is the kernel headers that the user is expected to provide and mount into the container. So the drawbacks here is that it's a long startup time, image, as you can imagine. User still needs to mess around with headers. We need to mess around with the code that tries to detect kernel headers for every distribution. It was actually, but it's not the best experience in our minds. And we wanted to improve. So the next step is we did slight variation. It's not really an improvement. Basically, a slim image. This is the image on the right here, which contains just this, the user's Go application, and it expects the user to provide the compiled eBPF object that they have compiled using the first container. So it's more appropriate to use this in production because the image is smaller. It's more suitable for production, but we didn't resolve any of the friction that we had. Still need to compile the BPF, still need to mess around with headers. Actually, we introduced more challenges. Now the user needs to think how to distribute the BPF to all of the nodes where they run Tracy. They also need to handle cases the fleet is not homogeneous, if it's not the same kernel version exactly. So we liked to move our code, the BPF code, to core, compile, run everywhere. This is a shift that we've made a while ago. This talk is not about that. I'm assuming you're familiar with that. If not, there's a wonderful post here by Andre that introduces the concept and how to do it. Actually, it wasn't a frictional experience for us to rewrite the file. We'll share some of the changes that we had, but in essence, it improved the experience for us because now we ship this container that has the CLI binary, the portable BPF object, not the code, but the compiled object, which is portable, and it will run whenever there's a BPF file available, and basically replace the headers external dependency that we expected the users to provide with the BTF external dependency. And you know how it works. The distro has if the kernel has a config debug in BTF flag, then the BTF will be available on syskernel BTF VM Linux, and libBPF will load it. So this also just works unsupported DOS or kernels. And some of the challenges that we had here, and basically this talk is about to share the challenges or the approaches that we took. It was first of all, now had a very strict requirement BPF. Tracy started the CC application actually in Python. We wrote it in Go BPF from IOVisor. At the time, Go BPF didn't support or didn't change signs of supporting core. Cilium wasn't ready for tracing use cases. So the easiest way for us to move forward was just wrap libBPF with our own Go library. We call it libBPF Go, and it's also a project we open sourced on GitHub. This is how a very simple Go application looks like with libBPF Go. We try to be more friendly to the developer, so it's struct oriented, it reads errors, it uses channels and all of the Go fancy features. And we like it, others it. We have communities who are using it and contributing, and we're very happy with it. So that was like
It died. Sorry, your sound is super choppy. I don't know, maybe try to turn off the video and turn it on or something like that, but it's kind of hard to follow sometimes. I don't know if that's bandwidth problem or not, but
I've removed the video.
So far, so good.
All right, I hope it will.
No, it actually is still choppy. Yeah, feel free to turn it on. And
yeah, I'll keep it off anyway. I'll try to speak maybe louder.
Okay, thanks.
Thanks for it. So libBPF Go was one problem that we see this way. The other challenge was that we now have this dependency of BPF, and user has this actually dependency, and taking from the libBPF mirror hub where BPF is actually available. We can summarize and say it's pretty much on any recent any recent we expect it to be available, but not today, then tomorrow for sure. But we need to remember we're a vendor. This is like when we talked about we have a different point of view. We need to support customers' older kernel well, and this was an actual challenge for us. So we thought about what if we could replace the system provided BTF with our own BTF. We will just replace the BTF with our own. So we looked at libBPF, and initially it was a little bit distinct. We saw that it's hard-coded looking from locations, but there was a session in the mailing list, and so there was a patch that did the BTF custom path option to the options, and that was great. This is exactly what we want to do, and we quickly added the support in libBPF Go as well. As you can see here, we pretty much pass it directly to libBPF. We don't really do anything with it, and this is how I can now load external BTFs. How do we generate the BTF to fill the gaps for unsupported kernels? So we can see here that let's basically just use PAHOL, can do the same. By the way, PAHOL for a lot of things, amazing. And basically PAHOL -J, exactly what we need if we can in the correct debug info symbols. So we wrote quick POC. We for different distros that we wanted to support for different versions, go ahead and find the debug info packages in the package repository. We extract VM Linux and convert it to BPF using PAHOL. And now we have this library of different BTFs for many different versions that we care about. And this library is what we now call BTF Hub. So this is a project that we spun off kind of this experience. It's on Aqua Security / BTF Hub, and basically go over a lot of different distros, a lot of different versions, get the info in different ways, every different distro, and using will generate the library of all BTFs. It's here on GitHub. The BT files are available on GitHub, so our client application, when it runs and it finds that it's hitting the VM Linux in the system provided path, it will just try to download the correct one from BTF. And this is how we are able to overcome this this one challenge. So we are on a mission now to kind of create a good coverage of different rows and configurations and versions that we care about. We also, appreciate your feedback to hear what you think about it. We actually, this is the term that we openly speak about, but people all around out and our friends at work already started using it or tried to use it in Gadget, their project. So again, we appreciate collaboration, back, anything you want to see. Feel free to experiment with and try to use it. So now Rafael can share a little about the challenge in actually porting the BPF code to be portable. Can we switch control to?
All right. Can you hear me well? Okay, so the idea here is to present some of what we think are the most common challenges for someone that is willing to turn a non-core eBPF application into a core one. Challenges happen not only because of eBPF peculiarities, but also because of legacy Linux distributions and their kernel support. We have split the challenges into those 3 sections, which I'll be covering in the next slides. So first challenge being explored is portability issues. Someone willing to create a portable application should be aware of. The road for someone to move from non-core eBPF software to core capable one would be to move from steps 1 and 2 to steps 3 and 4. If we want to maintain compatibility with older kernels, then BPF prog type tracing is not the way to go, as it requires kernels 5.4 and higher. And considering traces is still supporting 4.19 kernels, that is not an option to us. So let's say you have a non-core eBPF code and you make that move. This is when your eBPF application issues will start to happen. Whenever you start testing the same code base in different distributions and kernel versions. The initial issue will be likely your development model and testing environment. Simply compiling and loading eBPF objects, making sure that there are no verifier issues in your development environment does not necessarily mean that you're safe from other kernels verifiers troubles, and unfortunately they happen because Tracy needs to support many different kernel versions. We may need to tailor our software capabilities based on the running environment. So programs like Tracy might have to have reduced capability to keep compatibility with older kernels, but never lose the functionality. As you can see in this slides example, here we are reducing the amount of path components being analyzed in a path resolution unrolled loop. Depending on the kernel versions we're running at, this will reduce program size and complexity enough so the older kernel verifiers can accept it. So another challenge might be the use of tail calls. Its initial use case started to simplify complex programs by splitting them into smaller ones, or as a dispatch routing depending on the traced events, which is the case being showed here in this slide, as we have different dispatcher depending on the syscall types that we are probing, and they're all defined during in userland during load time. The good thing is that user space can build the program chains on the fly, and that bad thing is also that because it adds more complexity to userland. A quick parenthesis here, with the prog array recent auto population feature, we might not need to do that anymore, but before the eBPF program stack size limit was raised, there was indeed a need to have the tail calls a dispatch routing, even for the simple cases, as it would allow us to reduce the program's complexity. Alternative would be to rely in most recent bigger stack size limits by raising program sizes and reducing the tail calls complexity within our code, but we would break compatibility with older kernels. So Tracy chooses to keep compatibility on the tail calls and the tail calls complexity. Second challenge explored is libBPF support of all needed features. which, to be honest, is bigger than any other loader attempt. Because we have opted to create our own libbpf-based Go library, we must keep libbpf Go working with latest changes in libbpf. Some key functionalities to our eBPF application, like having the ability to detach all maps and reattach them on the fly, depending on the application business logic, might still suffer some changes before fully stable 1.0 libbpf API, for example, that must be addressed in our library sooner than later. So as an example, running CI in our code with every upstream change from libbpf is something we do. This example shows a tentative of another third-party project that also uses libbpf Go to implement the detach method for their needs without the destruction and disconnection logic in place for the in-upstream libbpf library. So when developing the legacy kprobe support, we had issues when trying to detach attached links if the perf event file descriptors were not closed, for example. This has recently been improved with the BPF link backed by file descriptors feature. But like any other new feature, we always have to seek backwards compatibility with our code. So our approach in libbpf Go is to have libbpf to support everything, and we just wrap it using cgo to reimplement, and we re-implement in pure Go things that we really, really need, mostly because of cgo performance penalty, like, for example, pulling file descriptors and things alike. In other words, we'd rather contribute to libbpf loader if missing any feature, and to solve punctual problems on our side instead of trying to reinvent the wheel. So currently, there are multiple BPF link attachment techniques being done by libbpf, at least about to be merged. When we first started using libbpf, it only supported perf event IOC set BPF attachment type. Unfortunately, in order to support 4.15 and 4.19 kernels, we needed legacy kprobe events interface to be supported. Andre already had a draft in the mailing list, and we continued that work. Currently, libbpf first checks if the running kernel supports BPF link create command to have the file descriptor for the link. And this has been recently added. And if the kernel does not support it, then it moves on into old perf event IOC set BPF call. If the legacy kprobe event interface is not needed, in our case for older kernels. So in order to have core capabilities in older kernels, two important changes were requested. First one, allowing libbpf to set current version attribute before the eBPF program was loaded. The second and most important is the legacy kprobe events interface support that I just talked about in the previous slide. And it allows the kernels 4.19 to have core-enabled libbpf apps. A quick note for anyone willing to use those, Andre has just simplified this code and added legacy uprobe support as well. So I would either wait for libbpf 06 to be available, or make sure to have latest patches backported to your application if you are compiling it statically with libbpf, like sometimes we do, or maybe most of the time. So here's a tiny pause to check on eBPF ELF sections, headers, and symbol tables. I won't spend too much time here, but since some people in the audience should be aware of, I'll just quickly describe some things. So differently than an object file produced by Clang or GCC to a regular architecture, let's say, it would contain sections such as rel-a, text, data, BSS. In eBPF object case, we'll have link time relocations made by libbpf before the eBPF programs are loaded in kernel. So each eBPF proc-bits section describes a program and needs different types of relocations depending on what type of data the eBPF program of that particular section is trying to access. Some relocations are kconfs, others are kseams. The first depends on kconfig variables from the running kernel configuration file, and the last is about the different data the eBPF program is trying to access. And then we have the regular, the usual eBPF elf sections to know of, but that is already probably known for everyone. So .btf, .btf.x, maps. Continuing, so the third challenge is a continuation of the second challenge, the libBPF support, but with a specific concern of kconfig relocations. When turning our eBPF software core enabled, obviously we sometimes missed some BPF helper calls, conversions, and similar things. So the next 3 slides refer to the same challenge, and they are connected. What happened here is that our core code would run just fine in all kernels above 5.4, but not in the ones below it. And after a reversed bisection, the commit in charge for fixing the behavior was related to BPF verifier, being thought about read-only eBPF maps having their values interpreted as scholars. So the verifier would do that code elimination correctly. In our case, the missing verification feature was kind of good because it made us realize we had a bug. If the OS did not have config arch has syscall wrapper enabled, the other branch did not have the correct core call, making the verifier to fail. Continuing in the same example. So we have fixed the issue by placing correct BPF probe read call to read addresses referring to arguments and registers. We have also proposed the verifier fix to 5.4 stable branch as it made sense, but it wasn't terribly required, but we thought it would be good. This also raised the question to us about having verifier fixes and things alike always being applied to stable branches, but I confess I have not digged into it, and I assume fixes are being suggested to stable branches as they make sense. And with that said, there's a bit more in this example still. If you see the kconfig symbol evaluation, we were using regular external variable that was having its symbol relocated by libBPF before load time based on the value being caught by the kconfig parser within libBPF. And we don't have that anymore. So the reason why we implemented an eBPF map containing values from kconfig variables instead of letting libBPF to do the relocations for us was that we wanted to get rid of proc config file dependency of libBPF, and by removing kconf relocation types, libBPF does not need the kconfig file to exist. This is not necessarily a corner case, but it helps in end user usability since eBPF software might be running as a container in a Kubernetes cluster, for example. Another thing to notice is that libBPF already does support external kconfig files apart from the regular OS ones, just as external BTF files for the BTF relocations. But unfortunately, the external kconfig files aren't able to replace entirely the OS kconfig file dependency. They are considered just as extra options on top of a must-have kconfig file. With a simple macro, we now have an approach that serves both core and non-core compilations, considering Tracy still has to support compilation during load time. And now the last challenge, the fourth challenge is also a continuation of the second one. It's the libBPF support, but with a specific concern of kseams relocations in all environments, even in those with old kernels. And that goes together with what Itai was saying. So after sorting all types of challenges, the last one was to have external BTFs implemented into Tracy in a way that the end user would not worry if running the kernel would have BTF data available or not. Tracy would be responsible to, through BTF Hub, download, if needed, cache, and use it from cache the BTF files for the running kernel. So this slide shows the initial call of Tracy downloading the BTF file for a hardware enablement kernel in Ubuntu Bionic. those kernels don't support BTF because Ubuntu Launchpad builders only rely in packages from the main archive, and they don't include latest versions of PAHO backported, as PAHO is included in the Dwarfs package, and that is considered quite important change for the distribution. There's a bug opened to solve that issue by having a more recent statically compiled PAHO binary available to build the hardware enablement kernels, but that bug has not been solved yet. Thus the need for BTF Hub, not only for Ubuntu, but for other distributions as well. Okay, so that's it. With all that said, I'll give the speech back to Itai, and thanks.
Can I have control back, please? Thank you. All right, thanks for that. So I just want to acknowledge other, I don't know, or maybe approach to solve some of these challenges. This is an example from Project Falco, which is another security tool. It's also an approach that we considered, and I want to address that. So basically, what we see here on the right is that they cross-compile their driver or probe to every target kernel that they support. They host all of those effects in the cloud. Then their actual application can detect the environment, go to this cloud-hosted repository to download the appropriate BPF object file that should be on the kernel. It's something we considered before BTF, and we actually, as you can see here, started to discuss with the folks, and also had a branch where we contributed support to make their build infrastructure generic, so that we can build and other eBPF programs in a similar version. And I wanted to address that, and now this list of kernel version-specific artifacts, before that seeing the same list of in BTF Hub, and kind of just think about it this way, where the Falco approach, where you cross-compile something to meet the target, you fix the artifact to meet the environment, essentially what cross-compilation does. And what we want to do with BTF Hub is, but the reverse. We want to fix the environment to work on the same artifact. And the benefit here is they can reuse always the same artifact. It's always the portable core compile once run over BPF code. Always the same BPF code, just maybe fix the environment if we see that we need to. So having surveyed all the journey that we've through from BCC, OBPF and libBPF Go, CORE, and BTF Hub, we wanted to also think about what's next in the public. And we don't really consider BTF Hub, Tracy with BTF Hub, I think it's not really truly portable eBPF application, because it depends on the BPF Hub to be available. So what could we do to achieve a truly portable eBPF application? A couple of ideas. One of them, as we can top, is to be instead of using a BTF file in Linux that contains all the types, maybe we can just have a BTF file with just the types that it needs. It's obviously a small subset than what's available in Linux, and using PAL, we can choose one or many different types that we about and expand them. It's actually usable, and then we create still a specific BTF file, but which contains just files, just the types that we care about. So obviously these types would be much smaller BPFs. VM Linux is quite small, but we account for the many different combinations of versions that we want to support, adds up. So this is one direction that we are thinking about. And the other, which can work, the first one or not, is to maybe reuse the same BPF files across different kernel versions if the types that we care about hadn't changed. So if we did the first step of application-specific BTF file, just diff those files and see if they changed or not, and if they didn't, just reuse them maybe. Even if we didn't and we still wanted to ship the full VM Linux, then we can diff the BTFs and see where were changes, and if we care to change it. If we didn't even use anything remote that relates to this change, maybe we can reuse the same BTF across different versions. So the first change gives us smaller BTF, the second one gives us significantly less BTFs, and potentially with both those changes, we can do kind of a truly portable eBPF application. So in BTF Hub, we state the kernel specific BTF files, but then create a BTF bundle that contains an application specific BTFs, which is so reduced so that one BTF can support a range of kernel versions. And the bundle would potentially be small enough so that we can embed it and ship it with the container or the Go application. And this is what we'd like to think about as a truly portable eBPF application. This is what we're experimenting with at the moment. If it works, we'll obviously share everything in GitHub, create maybe a script that lets you create a BTF for your application. But it's like a next step for us. All right, so if you liked this or find interesting in everything we talked about, feel free to engage with us. We're in GitHub, /Aqua Security, Tracy, or libpf Go, or BPF any one of those repos. We don't have a Slack or a mailing list, but we use GitHub discussions, so you can just discuss with us there. Or if you want to talk with one of the maintainers directly, we're on Twitter, so feel free to. We'll be happy to share ideas. All right, that's it. Thank you.
Thank you very much for the great presentation. Just to give a small recap from what was going on in the chat, Alexei and Lawrence found the BPF Hub idea really awesome. So it's great, and I hope that BPF literally doesn't take over the world right now, because GitHub will probably die from like all those binaries being downloaded in parallel. So we'll see how it goes. But yeah, if anyone has any questions, please go ahead. And unfortunately, I didn't have a chance to show this, but okay.
Hello, thank you for the talk. I really enjoyed it. Yeah, my next question was also going to be, how much traffic are you going to expect your BTF Hub to generate? Thank you very much for hosting these. One thing that I think I also talked with Andre about a while ago is that right now, like, I'm not very familiar with K-probes, but it seems like you use it a lot. So my question is basically to you. I think it's currently not possible to have a K-probe that is kind of compatible across arches, I guess. So like ARM64 versus x86. How do you fix that, or how do you solve that for your product if you support it? Do you have ideas how that could be solved, stuff like that? Thank you.
Prefer we don't.
Yeah, I couldn't hear
you. Not yet.
Sorry for that. I had both
right,
mutes. Okay, so most of the times we try to use the stable hooks, right? So from the trace points, and we're now trying to go through the LSM hooks for specifically, like, since we're dealing with security, we're trying to go through the LSM hooks now. But it's like what you said, you know, if we use the K-probes, then we have to make sure that we're considering all different kernels, and we have to deal with different types being used everywhere. So it's not an easy thing. That's why we try not to use them, at least until the last moment. That's it. No magic.
Yeah, so maybe that most of the hooks are into trace points or LSM hooks, and in the rare cases where we UA props, it's just we work.
So I guess one of the reasons for using like LSM hooks is because you know what are the set of hooks that you want to use, right? Like for tracing, the attachment surface is basically endless. That's a good point. I wanted to bring this up in my talk as well. Thank you.
And hopefully the distributions will catch up, so we don't have to do things as BTF hub anymore. It would be very nice so if you take, for example, Fedora, the latest versions, and Red Hat latest kernels, they already have backported all the BTF support. It's embedded, BPF and BTF features, they're trying to backport as much as they can. Some other distros are not catching up very quickly, so that's why we needed the BTF hub.
So I had a small comment about the kconfig. It's kind of interesting. I was expecting that like this override would work for you, but you're saying that because you don't have kconfig, it actually fails even when you provide your own kconfig. So no one ever complained about that. I think it would be completely reasonable to just say that, like if custom kconfig is specified and like the system kconfig isn't present, then like we should just ignore the absence of the system kconfig. I think that would be okay. Though, like it will differ. The behavior will differ between the systems that have kconfig or not. But I guess like when you use the custom kconfig, you sort of sign up for this behavior. I think should be fine. We can discuss that on the mailing list.
Okay.
And for the trimming of the BTF, that is a very interesting idea. I would go like half a step further. Like instead of just saying like, let's keep only like those specified types and maybe like related types as well. Why not say, let's keep only types that are actually core relocated from a given BPF object file, right? So the input will be like the full BTF and also your program, compiled program. I think it makes more sense to add it to BPF tool, honestly, because it knows more about like the BPF ecosystem in general. But at that point, it can fetch all the core relocations. It can figure out like all the types that are necessary and keep on them. So libBPF provides all the low-level APIs to do this pretty easily, either for Pahol or BPF tools. So it doesn't matter where it's implemented, but it's kind of not hard. Like so, give it a try.
Will do, definitely. Next step.
Daniel supports me in the chat. Any other questions from the audience?
There was a quick question on where do we get the kconfig files from. This is basically like from the host, and the idea here was we can mock some of the kconfig files. So for example, to consider config arch as this call wrapper is enabled, even if we don't know, sometimes we can just try to assume things, so. Well, thanks a lot, Dan.
Okay, thank you guys for the great presentation. It was very interesting, and it's good perspective, like how people deal like with the legacy systems, like where all those new and fancy features are not yet present, and you still have to work there. So awesome, thank you very much. So we have 9 minutes till next presentation, so I'll just put up this slide, and yeah, we'll start at 7:50. All right, welcome back, everyone. Please take your virtual seats, and we will start the next talk, automatically optimizing BPF programs using program synthesis. Sorry, I don't know how to say your name. Is it Chongwan?
Chongwen, yes.
Chongwan. Okay, yeah, please go ahead.
Yeah, hello everyone. I'm Chongwen, and the focus of this talk is to automatically optimizing BPF programs using program synthesis. Okay, I'll first introduce some basic knowledge of BPF. Maybe most of you are familiar with it, just to set the context. BPF is a technology to safely and efficiently extend kernel functionality. Users can write and attach BPF programs to different points within the kernel to do customized and high-performance kernel extension, such as networking, observability, and security. And this picture here shows where BPF program can be attached to process packets. Within the kernel, BPF programs runs in a virtual machine with RISC instruction set. The virtual machine has 11 registers and a stack. BPF programs may use key value maps that may be shared with other BPF programs and with user space processes. BPF programs may also call helper functions to invoke specific functionality, which is baked into kernel's code. And this is the BPF developer's workflow. Suppose our target is to write and execute a BPF program in the network device driver. First, we can write a BPF program in C and then use client to compile it into BPF bytecode. Then we can use a system call to load the bytecode. The bytecode then will be checked by the kernel checker, a component in the kernel that ensures the bytecode is safe. BPF enables unprivileged user code to run directly in the kernel context. Hence, the checker is crucial to ensure that malicious or buggy user code cannot crash the operating system or leak any privileged data. The checker proves safety by doing a static analysis of the bytecode. And if the bytecode is accepted by the checker, a JIT compiler here within the operating system will convert the bytecode into native machine code. Finally, the program will be loaded and executed within the network device driver. And the motivation of our work is that it's not easy to develop high quality BPF programs. There are two reasons. The first one is about size. Because the kernel checker must verify a program safety quickly, the kernel bounds the number of instructions it examines for each program. And on modern kernels, this limitation is 1 million, including examining the same instruction across multiple code paths. And in practice, even a program with a few thousand instructions may be rejected. To get such program accepted, a developer must disable some features or refactor the code by splitting the large program into smaller ones utilizing BPF tailcodes. The second problem is about performance. We'd like BPF programs to have excellent performance because at high rates, even small improvements can lead to significant CPU cost savings. One approach is to have developers manually optimize BPF bytecode, but it requires developers to be familiar with BPF, such as BPF instructions, the kernel checker, and the tricks to optimize BPF bytecode. If the program is long, this is painstaking work, even for something like a 5% latency improvement. Another approach is to use compiler support for optimization. However, this is lacking today because for the benchmarks in our experiments, higher optimization flag O3 produces the same code as O2. This isn't because O2 is already amazing. We identified several optimizations over O2 code. And this is the problem statement of our work. Can we automatically produce compact and more performant programs? The key challenge here is the tension between performance and safety. Next, I'll talk more about the challenge of how to improving the performance with safety guarantees. The kernel checker is stricter than needed. The checker's static analysis has many heuristics baked in to reduce the number of cases it needs to consider, and hence reduce the time to check program safety. So a program that's in fact safe may be spuriously regarded as unsafe by the checker. Here is an example. This program stores 2 bytes on the stack. However, it's rejected things according to the stack, according to the checker. Stack access should be aligned to the size of access. And if we modify the store address, it will be accepted. And this tension with safety makes it challenging to design compilers to optimize code. Traditional compilers match patterns over small portions of code and rewrite them into efficient code. In this example, the first instruction sets memory as 0. And the next instruction sets the next memory as 0. We can design a pattern to optimize these 2 writes into 1 write. However, such optimization are frequently incompatible with the checker's constraints. Recording the stack access alignment example we showed before, the optimization will be rejected if the stack access is not aligned to 2. And every potential optimization must also consider safety, since such safety constraints apply to many optimizations. Safety is a complex property depending on the entire prior execution of the program. It cannot be easily asserted for a peephole of instructions unless the compiler considers it a first-order concern. Being conservatively safe precludes many optimizations, while optimizing aggressively risks program being unsafe and hence rejected. We call this the phase ordering problem of the BPF compilation. Deploying better optimizing compilers require considering both optimization rules and safety constraints. Next, I'll talk about our solution K2 and how we use program synthesis to address this phase ordering problem. We design and implement K2, a BPF optimizing compiler, which takes client-compiled BPF bytecode as input, produce drop-in optimized bytecode. Over a set of realistic benchmarks, K2 improved code size, packet processing latency, and throughput relative to the best client-compiled program. K2 leverages stochastic program synthesis to optimize programs. K2 provides formal correctness and safety guarantees. We do this by encoding the BPF instruction set in first-order logic, including arithmetic and logic instructions, memory aliasing, control flow BPF maps, and some other helper functions. K2 formally checks equivalence between BPF programs and safety predicts over the program using logic. We introduce several domain-specific techniques that can produce equivalence checking time by 6 orders of magnitude compared to the naive formalization. Next, I will unpack why and how K2 uses stochastic program synthesis. Basically, program synthesis is a search procedure that automatically generates a program satisfying a specification. Our specification here is complex, combining correctness that is semantically equivalent to the input program, and the safety that is the program can pass the program can pass the kernel checker, and high performance. By considering them together in the search, we address the phase ordering problem. But actually, this program synthesis takes time to search the space of programs. So we are trading off compile time for better performance. Stochastic synthesis is a randomized algorithm to explore the space of programs based on MCMC method. The search is guided by a general cost function evaluated over programs. It's not the state-of-the-art approach to synthesis. However, compared to other approaches we considered, it's fast and generalizes easily to BPF optimization. Stochastic search can handle complex costs with complex constraints. And here I'll walk through an example, show you how to do this stochastic search. And so in the here, this is a cost contour chart. BPF programs on the same line have the same cost. Cost contours can be highly complex with many local optima that are actually globally suboptimal. We can start the search from the input program, this green one, and each program has 4 costs: performance, error, and safety. The total cost is the sum of these 3 costs. At the first iteration, we move to a proposal by modifying the current program at random, this one, and we will compute the costs for the proposal and the maximum acceptable cost. Since the new cost is larger than the maximum cost that can be accepted, this move will be rejected. And at the second iteration, a new proposal is generated. Since this proposal's total cost is slightly smaller than the acceptable cost, we'll move to the new proposal. And it helps the search, even though it has a higher cost than the current program, it helps the search escape from the local optimal to find the global optimal. And at the third iteration, a new proposal is generated, and its cost is smaller than the current program, so it's accepted. And at this iteration, a new proposal with a smaller cost is generated. So once again, we will move forward. As we can see, with more iterations, we can get programs with lower and lower cost. And here, I'll talk about the overview of K2. At a high level, K2 takes a BPF program as input and produces optimized eBPF program as output. The given input program is the first program for K2's stochastic search loop. At each iteration, K2 performs a small random modification to the current program to generate a new program called a proposal. And then K2 computes the cost of this proposal. The cost is a combination of correctness, safety, and performance. If the performance cost is at most slightly larger than the current program, it will be accepted. And this proposal becomes the next program used as the base for modification within the search loop. Whenever this proposal is accepted and it is safe and equivalent, it will be added into a program database. After a configurable number of maximum iterations, K2 will rank all the programs in the database and emit the top K programs according to the performance. These programs are all correct, safe, and have the best estimated performance. Next, I will introduce how we compute the cost in this search loop. Here we have 2 performance goals: fewer instruction count and better throughput and latency. For the first goal, we use instruction count as a performance model. For the second goal, we use program estimated running time as performance cost. That is the sum of each instruction's measured running time. Program interpreter here is used to quickly check whether a proposal is unequal or unsafe by utilizing test cases, which can speed up the cost computation. And in the next few slides, I'll introduce how the equivalence checker logically checks whether a program is semantically equivalent to the input program. If two programs are semantically equivalent, it means that given the same input, two programs will produce the same output, and this property must hold for all inputs. Let's look at an example. For BPF programs, R1 and R0, R1 and R10 are input, and R0 is the output. We can easily find that if R1 is not equal to R10, the outputs are different, meaning these two programs are not semantically equivalent. Now the question is, how do we do this in general? We do this in first order logic in the theory of bit vectors. Here's the logic of formula. We set the same input to two programs and encode the two programs' logic to check whether it's possible to imply that two programs produce different outputs. If the formula is unsatisfiable, it means that there's no input that can make the outputs different. If the formula is satisfiable, the logic solvers will return a counterexample that is a single input, which can cause the two programs to return different outputs. I'll use an example to show how this works. First, R1 and R10 are the same for two programs. And then, according to program 1, R0 is equal to R1. And according to program 2, R0 is equal to R10. And finally, we set that R0 from program 1 is unequal to that from program 2. And we set this formula to the SMT solver. And for this example, the solver's answer is set, and it will produce a model which is a counterexample to show that for this, if we use this counterexample as input, these two programs will produce different output. And so here in this example, we can see that the instruction logic is easy to encode. Formalizing program behavior in logic requires formalizing each instruction opcode of BPF. This is tedious but straightforward for arithmetic and logic instructions. However, handling memory access instructions, branching, and BPF helper calls is more challenging. And you can find how we deal with them in the paper. In the next few slides, I will talk about how we accelerate equivalence checking to make this synthesis practical. Equivalence check takes a long time, so solving time grows quickly with instructions, branches, memory, and map operations. For a benchmark from Cilium, the equivalence checking time is over 24 hours. So if we would like to complete this synthesis, it may take maybe like 10 years. So our question is, can we reduce equivalence checking time to make a K2 complete optimizing in a reasonable time? And we reduce solving time by reducing the complexity of first order logic formula. The first method is to concretize some symbolic executions within solvers, which has the effect of assigning concrete values to some variables in the formula. We can achieve this through careful static analysis. K2 can infer the memory and the map type, most memory access offsets. This can reduce the solving time to 1 minute. And the second method, the modular verification, decomposes the large verification tasks into smaller tasks. This is used to deal with long programs. This method can further reduce the solving time to 7 milliseconds. And I'll introduce the second method through an example. Suppose we wish to check program. Suppose we wish to check program 1 is equivalent to program 2, and suppose we know that the two programs only differ in instructions within the red highlight window. We can simplify the check by directly comparing the instructions in the two windows for equivalence. Firstly, we need to figure out what are the output variables to be compared at the end of window. And our key insight is to only check whether the registers which continue to be live beyond the window are the same after the window, not all program registers. We can infer the live variables from the postfix program. That's the part of the program after the window. And here, according to the execute instruction, R0 is the live variable. And according to the next instruction, R0 is equal to R3. We can remove R0 from the live variables and add R3 in the live variables. So as we can see at the end of this window, the only register we need to check is R3, not any other registers. However, the result here is that the window 1 is not equal to window 2 if R2 is not equal to R1. And we achieve this by infer some input variables and preconditions from the prefix program. According to this prefix program, we can infer that R1 is equal to R2. They are both equal to 0. So we can see that these two windows are actually semantically equivalent. And to summarize, modular verification checks the equivalence of two windows of program rather than two full programs. We infer variables live out of the window and precondition over variables affecting the window. The final formula we discharge to the solver is shown here. It is very similar to the full equivalence checking formula, but with stronger preconditions and weaker post conditions. Finally, we look at the problem of computing the safety cost. Safety cost in K2 are either 0 or a maximum value. And we have checked some general and specific constraints enforced by the kernel checker. We designed several techniques to perform this check. We statically analyzed the code to quickly detect some unsafe proposals. And then we use first order logic formula to logically check the safety. This generates safety counterexamples if the proposals are unsafe. And these counterexamples can be used by the program interpreter as test cases. This can quickly eliminate unsafe programs without an expensive solver query. And as for kernel 5.4, for all the programs we tested, it's always the case that the safety checker in K2 always produces programs that are safe according to the kernel checker. Next comes the evaluation part. We evaluate K2 in terms of two performance goals: program compactness and program performance in terms of latency and throughput. We use K2 to reduce the number of instructions for 19 benchmarks. Here's a part of results. We compare K2's results with the best client version. The comparison ranges from 6 to 26%. And the average compiling time is about 22 minutes, excluding the largest program. And we use the following setup to measure the throughput and the latency. Firstly, we load the BPF program to be measured in the network device driver of the device under test. And then we use T-Rex to generate high-speed traffic. These packets are processed and forwarded. This packet will be sent to the device under test and then be processed and forwarded back to the traffic generator. Thus, we can measure both the throughput and average round-trip latency with high fidelity. And this is a graph of the rate of receiving packets, Rx rate, across different rates of sending packets, Tx rate, for one of our benchmarks. The x-axis is the sending rate, while the y-axis is the receiving rate. We read the throughput when the sending rate is at the maximum loss-free forwarding rate, which is the point where the Rx rate tapers off with growth in Tx rate. For this benchmark, we can see that client 01 has the lowest throughput, and then client 02, 03, and K2 has the maximum throughput. This table shows the throughput improvement of 6 benchmarks running in the device driver, and the gains ranged from 0 to 4.75%. This is a graph of average round-trip latency in different packet sending rates for a benchmark. The x-axis is the packet sending rate, while the y-axis is the latency in microseconds. We measure latencies in 4 packet sending rates. The first one is when sending rate is low, smaller than the throughput of all versions. We can see that K2's latency is a little bit smaller than client. And the second one is when sending rate is medium at the lower throughput between the best client and K2. K2's latency is much smaller than the best client. The third one is when sending rate is high at the higher throughput between the client and K2. We can see that K2's latency is still much smaller than the best client version. And the last one is when sending rate is higher than all versions. We can see that K2's latency is a little bit smaller than client. Overall, for this benchmark, all K2's latencies are smaller than the best client version. And we use this way to measure 4 benchmarks. The reduction is from 1 to 55%. To understand the evaluation numbers, we cataloged optimizations that K2 derived automatically. You can find a detailed list in the paper. Here are 2 optimization examples found by K2, and K2 is that to reduce instruction count. The first example here combine 2 writes into 1 write, reducing 2 instructions. And the second optimization comprises the program by leveraging the context of the window within the program. K2 used the value of R3 written in a prior instruction to optimize the window. Next, I will conclude our work and discuss the future work. In summary, we presented K2 an optimizing compiler that produces program with reduced size and higher performance. K2 contributes several domain-specific techniques for synthesis and verification of BPF programs. Looking forward, we believe that synthesis is a viable approach to optimize BPF programs. And here are some questions we wish to explore further. We'll think about how to optimize large programs fast. The current result shows that optimizing large programs can take much longer than a few minutes. We want to reduce the optimizing time to make it practical to be used in the production system. We found that the key challenge K2 faces is that the search algorithm spends too many iterations. That is time in trying to optimize parts of the program that are already or close to optimal. We have some ideas on dealing with this, such as restarting the search if it takes too much time, selecting effective instruction sequences that have the highest potential to be improved. The second one is to explore how to generate safe and efficient code for other infrastructure, such as SmartNIC. And the focus of this work will be design a better model to estimate program running time, since different architectures have different running time even for the same instruction. Our current program running time model is simple, just as the sum of each instruction's measured running time. We'll design a more precise model for program's performance estimation, which considers the sequence of branches that are taken and the number of interleaving of memory accesses. The last one is program repair. This is to help non-expert users to fix the unsafe program, which is rejected by the checker, to be accepted. The checker's rejection reasons are not always interpretable and actionable for developers, since BPF are often written in high-level languages like C, while the checker's log is at BPF bytecode level. Also, there's no explicit documentation of the checker's general and specific safety rules, except the source code itself, which is more than 10,000 lines. The goal of this feature work is to automatically generate program repair suggestions for unsafe programs. We are thinking about using safety counterexamples generated by K2 to synthesize safe programs and select top K safe programs whose semantic is closest to the unsafe program to be fixed. And we are seeking for ideas for improving K2. Firstly, we are looking for benchmarks that you struggle with. For example, some programs whose program size or performance is crucial to the system. Also, we want to get some real-world feedback on how quickly a compiler like K2 should return results to the user, and how frequently do your CI and the deployment pipelines need optimized binaries. Interactive response time needed, or maybe like returning a result after 15 minutes is sufficient. The next one is about safety rules. We added K2's safety checks one by one after filling the checker. How could we enhance and redesign K2 to keep up with the evolution of the kernel checker safety rules? Could safety rules be expressed in a common high-level language that can be compiled and executed both within K2 and the Linux kernel? One of the main reasons we developed our safety rules is that we want to use the safety counterexample to prompt unsafe programs. Could the kernel checker be enhanced to provide some counterexample inputs? The last one is, how do you think of K2 and our feature directions? Are they useful in real production systems? Broadly, are there things you think that we could do now that we have all this compiler machinery? Yes, and thanks for your listening. Here's our website, and if you have any questions or feedback, please contact us. Thank you.
Thank you. John, you had the biggest and most questions. Do you want to ask them live? Or should I just read it?
Yeah, sure.
I
I can summarize it, so you don't have to read it. I guess my sort of overall thought when you were talking about the kind of gadget you found, right? The one with the 64-bit, or sorry, the 32-bit converting to 64-bit, is could we use K2 because it takes so long in the runtime to find the gadgets and then encode the gadgets in the people optimizer on the back end, right? Because it's not always obvious as a sort of backend BPF LLVM developer what optimizations are even useful for programs. So, if K2 could be used to sort of scan real programs, figure out what optimizations are useful, then we could put those in the backend, and you wouldn't need to run K2 on all the programs just to find the sort of common set of these gadgets. But I don't know. I mean, the question I guess there is is that a feasible thing to do? And do you find sort of a stable set of gadgets across different programs, right? Or is it like every program finds something different?
Yeah,
make some sense?
Yeah. So it's a good question. Actually, we have a detailed list of these optimizations discovered by K2 in our paper at the end of paper. And so actually for each program, there are some common patterns that can be used. You can like manually encode these optimizations. For example, like here, combining like smaller memory access into some into bigger into longer right. But the issue here is that for some such optimization, some patterns are not that clear. For example, for example, we need to consider whether, like for stack, we need to consider whether the address, store address or load address is aligned to the access of the size. And if there are some complex memory access, for example, we would like to exchange the higher 4 bytes to the lower 4 bytes. It's not clear to me like how to find such pattern and optimize such pattern. But for some like straightforward pattern, definitely we can like write this in LLVM. Does this make sense?
I think it would be. Yeah, that makes sense. I think it would be interesting is if like you took the collection of ones that are sort of straightforward to put in the backend of LLVM, and then kind of rerun K2, see what you find, and then see if the performance improvements are, right? Because I'm trying to understand like what gadgets are costing the most and which as far as performance goes, right? Because right now you kind of have them all lumped together. It will be like this specific gadget, if I got 30% of them, maybe I get 50% of the performance. Anyways, the talk overall was super interesting. I'll go take a look at the paper. Thank you.
Thank you.
Mm-hmm.
If I can just add to that, Srinivas Narayan here. I'm one of the other co-authors of the paper. So yeah, definitely there is, I think, an interesting study to be done with respect to understanding which optimizations give you the biggest bang for the buck. Just also want to point out that there is like this whole class of context-dependent optimizations that really requires a lot of knowledge about the program. Like say example 2 on this slide that Chongwen's showing here, like is actually an example of that. Like so those would be somewhat, I think, more challenging to encode in a program, because you really have to build up some amount of static analysis before you actually know that, okay, given these conditions that existed in the prior part of the program and these other sort of computation that happens on the result of that particular window, you could actually do that optimization safely and correctly. So those would be somewhat more challenging. But I think the question here is like, what is the performance gain from each of these different classes, which I think would be useful to measure. So yeah, thanks for that question.
Just from the chat, there was also a question that the paper presented results based on Clank 9, and Florian asked whether you guys tried to do it like on the latest Clank versions, and it seems the answer was no. Is it right?
I'm still. Yeah. We only use Clan 9 to in our experiment. We haven't tried other Clan versions. Is that your question?
Yeah, I guess people implied that newer Clanks probably have better optimizations overall, so it would be good to double check like which of the discovered optimizations are still like not implemented by the Clank. I think that's sort of the implied.
Yes, it's a good idea. We will definitely try latest version of Clan to see the optimizations implemented in Clan. Yeah,
it also seemed like Alexei wanted to make some confession. I don't know, Alexei, do you want to explain what you were trying to say about the BPF ST instruction?
Sure. Sorry. Yeah. So like, it's actually it's nice confirmation that ST actually produces better, like faster code, because smaller code not necessarily better, right? So in this case, well, from 3 instructions, like on this slide, it compacts it to 1 instruction, but it's a question whether this instruction is actually faster on x86, because every like x86 as the main target is CISC. And once the CPU converts it to the micro-ops, the number of micro-ops for these 3 BPF instructions on the left in example 1 and one BPF instruction on the right is the same. It's actually like on x86 micro-ops, it's the same number of micro-ops. So the speed sometimes is equivalent, right? So it's wasn't, well, and also like from LLVM side, it was easier just to like emit the STX instruction instead of ST. So that's why like we had a discussion like on and off whether having it makes sense, but just folks didn't do the analysis across different benchmarks to see whether this particular optimization like makes sense. From your data, it looks like that we definitely need to like accelerate this analysis and make LLVM emitted because it looks like it's useful. So yeah, thank you so much for doing this.
Yeah, thank you. And actually, there are 2 goals in our papers. The first one is reduce instruction count, and the second one is to improve the performance, like latency and the throughput. So for the second goal, we needed to design a performance model to show the estimated running time of a program. And now our current model is simple, just the sum of each instruction's measured time. And if we can explore a better model that can more precisely estimate the program's runtime, the results would be better. I mean, like maybe some programs with more instructions, the running time of such program is smaller than the program with few instructions. This could happen depending on how you design this performance model.
Do you need to have a performance model though? Could you like try it on x86 and see if the optimized program does better, and then we could, I mean, from my perspective, if we were to use some of this, it would be nice to have some tools that you could run with, get like an output back, and then see perform an A/B comparison of the optimization program, and then use it as a runtime optimization tool rather than using performance models or something.
So for now, we just use a simple model to estimate the running time, and then test them in the real experiments. I mean, just run in the real production system. So we haven't tried to design a better model to taking branching something else into consideration for x86 architecture. Yeah, but we'll do this later.
Yeah, I think in general it would be nice for you academic folks to interact with us lowly engineers on making this practical and having practical wins. So for example, for all the XDP programs, right? If you were able to speed them up up to whatever 5% or something, that's huge difference in practice, right? So if you can provide some tools for engineers to actually test this. So to KP's point, right? It's not always too easy to design benchmark in the vacuum, right? Usually you have specific program and you know how to test it in production on some small proportion of your fleet, right? So I guess the biggest problem here is can you give us tools like this K2 as a separate binary or whatever that we can just use on existing programs and see what actual difference it is, and then we can analyze the generated code differences and stuff like that. So I guess I'm just encouraging you to just not just publish the paper, but also interact with us on the BPF mailing list and
Yeah. Actually, we also wanted to test K2 in your real production system to see how it works. Yeah.
Yeah, I guess the goal here, the key here is make it simple to try this. So yeah. Chris had the question. Please go ahead.
Yes, I actually was interested on whether what basically the impact would be in comparison, for instance, with the GCC toolchain, since that now also supports compilation for BPF. because it has obviously different ways of how it does optimization. And I could foresee that the work you're doing here and the results from that would definitely be very beneficial to make improvements on that area as well. So that basically, we have more than one tool chain that can support BPF and really benefit from this.
Yeah, we haven't tried GCC. Yeah, but we can
Yeah, I think going forward, like trying GCC, is definitely on our radar. So yeah, I think thanks for that suggestion. I mean, we do want to kind of try this out with, I think like both with different versions of Clang, and with GCC, and this could potentially be a way to kind of unearth the, like new optimizations basically that could then be sort of integrated into the backend. So yeah, I think that's we will definitely kind of look into that. Thanks for the suggestion.
Okay, thank you. It's great work.
John, you had a question.
Yeah. I just had one more thing to add. I think is like you were worried about the running time, right? Is it usable? I would maybe just add, like, from a production side, if it's 5 days to run in the background and I get a 5% win on my XDP program, I'm going to do it. So I would worry less about the runtime, right? Because this is something that's happening on some box in the background, right? So for me, it's more about the performance. I don't mind taking the little gadgets and then pushing them into my program after the fact. Right? So just a bit of feedback is I would worry more about like reporting the gadgets concisely in a way that's readable, and maybe running time is nice, but it's not the sort of the end necessary, I would say.
Got it. Thank you. Yeah.
Thanks so much.
Daniel, your turn.
Yeah, it's really awesome work. Thanks so much for presenting this here. I also had another question in terms of the optimizations that you found. I was wondering, maybe like some of the patterns that K2 generated, maybe like they would more ideally map to native x86 instructions, for example, or ARM64, but BPF doesn't have them because it's more constrained. And if there's like a potential, given they have a speed up, we could also add new BPF instructions for that we can then more easily map in the JIT backend, So it would also be useful to look at that as well, I think.
Yeah. Thanks.
Daniel, just want to understand your suggestion a little more carefully. So we performed all our measurements on x86. So are you suggesting that if we find common patterns across x86 and ARM, that would be useful? So that could be one way to interpret your question. The other way to interpret your question is maybe there are common sequences of instructions that could be combined into maybe a new BPF instruction at the bytecode level, which could then have a more efficient JIT. So I wasn't sure which or both. Yeah, go ahead.
I basically meant the latter, because like BPF instruction set is more constrained and less complex than others, but maybe there are patterns generated from the compiler that would more easily map to the native opcode if there is something that could be used directly for that, right?
Got it. That's a really good suggestion. Yeah, thanks, Daniel.
Yeah, so we have 1 more minute to the next talk. If anyone had some quick question or remark, now is the time, and then we will have to move to the next talk. But yeah, I do encourage you to just follow up on the mailing list and like discuss like specific next steps. Like as John said, like in practice, like even 1% makes huge difference. So even if you have to run it for 24 hours just to like optimize one variant of the program, probably in a lot of cases it makes sense.
Yeah, got it. Thank you. And also we are in like CDN eBPF Slack channel. So if you have any questions, feedback, you can DM us, and also you can contact us through this email. Yeah, thank you.
Thank you very much. And just in time for KP to start.
Thank you.
When I find you in the list, yeah. Go.
So, sure, is it time to start? Yeah, it's actually exactly 5:40 here. So we're going to talk about BPF and security at Google. And the stuff we're going to talk about is why did we introduce atomics? What are we doing with atomics? And a trick that we learned is called promises. Some more tricks about how do we chunk data and how are we using the BPF ring buffer. The interesting bit and the open-ended bit of this presentation is like what's next for BPF and security auditing. There are some interesting challenges there. And actually, what are we missing for implementing policy enforcement policies? And these are mostly advanced policies and stateful policies. So we're going to talk about why did we add atomics to BPF, and it was primarily a use case driven project with, and we have a couple of interesting notes on our use case. And the use case, the broad class of problems the use case boils down to is easily generating UUIDs in parallel in BPF. And our use case is that some of our events are very large in size. So imagine an argv coming from the kernel that is 6 megabytes. And you have a BPF ring buffer that is also probably 4 megabytes in size. So single argv could like completely overrun your BPF ring buffer. So the blue thing there is the BPF ring buffer, and the red thing is the tail end of the argv that just doesn't fit on the ring buffer. What we decided to do was that we said that we're going to chunk this data, and this is not just arguments, but any sort of large events. We're going to chunk it into smaller pieces, and we will use unique IDs to connect these chunks. And essentially, the first event says you're going to receive a bunch of new events from the user space, which user space is going to wait for a certain amount of time and collect all these events that have this promise ID. And now what this gives us is that if the big event comes, right, and the ring buffer, the user space can start processing these events as soon as the first event is written. It doesn't need for the whole event to be written. Also, you're not limited by the whole 6 megabyte versus 4 megabyte challenge here. What you can also have is that you can have multiple events being emitted from different hooks. For example, that when a kernel module is loaded, you can have an event emitted with the promise, and further down the syscall, like tracing the kernel, you can emit more events that connect more data to this. So and you can build this up back in user space. So we call this asynchronous communication, and the first header comes from the program, and it has a promise ID. You can store the promise ID in task local storage and further down the hooks. There are some limitations with the task local storage approach here, which we are trying to solve with the lack of availability of task local storage to sleepable programs. There's a patch set out there, and I think Martin has given me interesting feedback. It's just waiting for another iteration. We should get that in as well. The next thing is that why do we like the BPF ring buffer? And this is something pretty nice. The first thing the reason why we like the BPF ring buffer is it scales better with respect to the number of CPUs. And what we notice is that it gracefully absorbs the spike on a single CPU. So with a per CPU buffer, when you have a spike of events on a single CPU, for example, with executions, one buffer tends to get full, and this is the per CPU buffer can be interchanged with perf buffer, which is the previous mode of communication from BPF that we were using. And like one buffer gets full, the others remain empty, so you have an ineffective utilization of the space you have when you have a burst of events. The other thing this plays really well with is the ordering guarantees and the promise system that we just talked about. Because the BPF ring buffer gives you better ordering guarantees, you have a simpler user space logic when you have to construct back these chunks of data that are arriving back from the kernel and user space. Another good part is the customized watermark logic, which if you've used perf, you might have noticed that the perf has a flag that or an option that says watermark, which is primarily based on the fullness of the buffer. So you can say that don't wake me up if I'm more than 50% full. If I'm less than 50% full, wake me up only after a certain percentage of fullness. Whereas the logic in BPF ring buffer, you have helpers, and the helpers allow you to check for fullness and other parameters. So you can decide whether you want to wake the user space at this point or not. This is pretty nice. And the other thing is the isolation or the parallelization is semantic. You can say that I will have multiple ring buffers for different types of events, so that you can't have one event starve the other event. And you're not forced by this forced sort of CPU-based parallelization, which sort of plays into the point number one, or the first benefit we talked about. So yes, BPF ring buffer is awesome. Thank you for implementing it. We talk about the ring buffer chunking trick, essentially from the for how we chunk argv is a simple use case extension of the overall chunking trick we talked about last time. The chunking is done on a fixed size based chunk. The verifier likes to know the size in advance, but if you start allocating the maximum possible size that the verifier expects, you get like terrible utilization on the buffer. So you break the large data down into fixed size chunks, but the total number of chunks you might emit for a particular event or a particular argv, those remain variable, and then you can control based on the max argv size the max chunks that you might emit for a particular sort of event. This is nice. We had some cool discussions in the past about enabling variable size messages on the BPF ring buffer. I don't think that is really needed because we were able to overcome with this, but it may be worth discussing if we need it in the future. So there were really cool ideas that we have probably in one of the BPF office hours. And if you folks have these use cases, we could discuss it in the micro conference as well. So this is the more interesting and open-ended part of the discussion that we wanted to bring up here. So what is next for BPF security auditing, and what is actually missing? So we've been using, the first time when we pitched the BPF LSM, we sort of said that you can do auditing and enforcement are two facets of security, and then you should be able to do both using BPF LSM. And as much as we would like, this is not really the reality on the ground. And I'll give you some examples. For example, it really works well for process execution. The BPRM committed creds hook just is in the right place, has the right arguments, and to sort of log process executions. So there are no issues with that. But for example, with mmap, the LSM hook is missing the VMA data structure. So what we do use currently is the classic perf. This is not to do with BPF. We are not attaching any BPF to the perf hook. And the problem here is the classic problem with anything that is not BPF. It is you can't customize it. And also it is missing some data. So for example, if I wanted to add the parent process start time, because some of my logic relies on that, I cannot do that without really changing my kernel and the perf tool and so on. Another example in this area is the socket operations. And this is the thing that is missing when the LSM check happens is the port. And we try to solve it by a mix of exit hooks, which is fine, but it comes with a maintenance overhead. And actually knowing which exit hook to use here is the real challenge. Like you spend multiple hours with multiple like developer cycles figuring out what exit hook you should be using. A similar scenario with module loading. When the LSM check happens, you're missing the name of the module, and there's a trace point. This is a BPF trace point, but again, this trace point is still missing some data. So we have to again do the dance with fexit hooks and trace points together, chain them together with a promise or with some BPF map. So the theme of the problem is that when we typically do enforcement early in the state of the object or versus the operation, and audit typically happens late. So that's the common theme that we've observed with the LSM hooks. Now, there are some solutions, there are some options that we have that we can do, but the current state is that there is no clean and flexible surface that we can attach to. Now, we have the LSM that provides a small sort of confined surface that we can use. We can also do the same thing with probably fxit hooks or fmoderate hooks, but this LSM API, I would rather not call it an API, but the LSM surface represents the knowledge that the LSM developers have captured. And when a developer looks at these set of hooks, they know that these are the security relevant hooks that I need to look at. And it's a these are the valid places where I can enforce some key security decisions. So the question that we need to ask ourselves is that do we need a special surface for auditing? And this is to capture the value that has been created by auditing experts and existing auditing frameworks in the kernel. And there are a couple of them that already exist here and there. So this is what it looks like for the LSM before and after. A common BPF pattern takes something that was previously configured by a rigid language, needing kernel and user space changes when you want to add new features. Now you can do that with a simpler BPF program. You can get that inflexible policy engine out of the way, and then you can maintain your own customized user space code. eBPF rocks in this area. It's the place where you're supposed to use that. And the other point which I would like to mention is that I previously alluded to is the smaller attachment surface or the selected set of hooks. This also plays into like the talk by Ite that about when you want to select a certain number of hooks that you want to get BTF information for or report, this is a nice surface or a subset that you can select. It also allows you to write helpers because the places at which these hooks are, they have they have better guarantees than all tracing hooks. So one option we have here is add new LSM hooks at the places that we just mentioned. Like now, these LSM hooks are primarily for bookkeeping, and now there are some hooks in the LSM hook, sort of the list of LSM hooks that are primarily for bookkeeping. They are for Plumber state management. Some hooks are actually introduced very specifically for certain LSMs. Now, the benefit of this approach is we already have BPF probe type LSM. We have the mechanisms to attach it. The con or the discussion that will appear here is that they're not tied to an existing MAC policy. Now this may be tied to a MAC policy in the future based on if you want to take a late decision given the extra information you have. But you need to add, this is going to come up and be discussed to death if we go with this approach. Now, we do have another system in the kernel that is for auditing. And similar to the LSM attachment surface, there is the audit API, which has an audit user space. The audit user space has a policy or a config language. The output format is strings. Can we use this audit surface, add the BPF goodness to this, and sort of alleviate the inflexibility of the config language and the output format? So in theory, yes, we can do that. But when you look at the code, the amount of work that is required is quite large. The audit system has a rich set of auditing points. The way they're structured is quite not BPF compatible. So the data comes from this thing called audit context. This context is again inflexible, so you'll have to change the audit the fields. It's a union of large number of basically syscall arguments for their events, and the functions that it attaches to, the audit callbacks, are sort of all inlined. So extending BPF would be a considerable effort, like essentially a major overhaul of the audit framework. And people may also have config audit turned on or off based on their performance sensitivities. So another option we have is use the perf subsystem. Now, perf is an interesting mention in this area. I mean, it's called perf, but it really does a lot more. And I think people who use perf are aware of it. And actually, as it turns out, that perf is very nicely suited for this audit use case. The perf has an existing API for the mmap event. Actually, the perf event mmap call in the kernel is exactly in the place where we would like it to be. Perf has another interesting event is like changes to kernel text when namespaces are created, fork, exit, and exec events, and also BPF programs on loads and unloads. The sad side here is that ftrace C flags are disabled on all of the perf functions. So like in kernel events, like whenever you compile the perf code, you need a particular type of C flag, which gives you an extra 5-bit NOP in the code so that ftrace can attach to it, which is also used by the BPF tracing mechanisms to attach. And those are currently disabled on perf functions. I try to dig into this. I try into the patches that probably have added this, and there were two sort of reasons that appeared, like a fear around sort of the recursive sort of you trying to perf its own functions, and the other reason that appeared was the fact that there may be some M count overhead. I think the M count overhead in particular can be solved by like there is an event filter that basically exclude certain functions from this mcount profiler framework, and we could just make these functions as default in the mcount. So perf underscore star as default in the in this setting. For the recursion thing, or we could also limit the number of functions we can attach to here. So this is one possibility. The other possibility is like make it extensible via BPF. The thing we talked about. The thing we talked about similar to the audit and the LSM use case, and there was already a talk in BPF in the micro conference about extending perf with BPF, and you add a new BPF surface there. Now this has the benefits that the perf events are in the right place, they have the right arguments, but there is some inflexibility here. Do we implement whenever we need to add a new event or a new audit event to the perf API? Do we add the corresponding changes to the perf tools and stuff? So there will be two systems that will need to go hand in hand. It's not necessarily a bad thing because it also gives you nice already pre-existing tooling that you can attach to, but it is something that is worth considering. It's a higher bar for adding a new event in this API. So I'm going to leave this talk more as an open-ended discussion for some of the things we talked about. So it's going to be a shorter one. But let me go into, before we end this, I'm going to talk about, in short, what is missing for advanced enforcement. And the stuff that is missing for advanced enforcement, like if you've ever used SE Linux, what SE Linux does is it sets extended attributes on file system inodes of files, which SE Linux calls security context. And when when certain operations happen on the inode, or something that is reading an inode or transferring the security context into another object, this information is read. Now LSMs call this security labels, and the main function is that you can persist this policy. You can tie this policy to the object, and you can persist it across reboots easily. Now, the problem is that BPF LSM cannot write or read X address easily. So we need some helpers there. I don't think there's anything difficult to implement. I've not read into what the detailed signature of this helper would be, but at the very minimum, we would need access to like BPF get X adder and BPF set X adder here. So I think that's pretty much it from my side. And I would like to open it up for discussion on what we could do in some of these topics to make BPF audit a reality.
Great, thank you for the presentation. I guess we'll start with John Fastabat. He has 2 questions.
Hey, I'm back. I think the first one was just about just a question or a statement, I guess, about the chunk size. I just noticed, like in general, they could be interleaved with other chunks, so supposedly you ID them somehow. But this is, I think, minor.
Yeah.
What I really wanted to understand was, like, for the audit, why can't you just use the kprobe hooks that we have and hook any function and probe read all the data you need? I missed something.
So I think this is the developer experience thing, right? Because you know what kprobe to hook at, right? And this is why we didn't see the LSM. People had fmod red programs all the way, like the people could use them for security as well. But when you have a limited surface, when I know that these are the 100 functions, 100 is actually too large a number. These are the 10 hooks that I can hook at for auditing certain events. The barrier to entry there is a lot lower. And then you know that because these functions are like, from a kernel developer perspective as well, you know that these functions are in like, they're not running in an atomic context or an interrupt block or something like that. I can provide some extra helpers there. Whereas in tracing, you have to do this mess, right? You create a BTF set ID for each helper, and then you start adding like allow lists for that. I think it's the whole experience of clearly clarifying that this is where you want to audit. These are the events that are available, and then you keep adding new places.
Doesn't that feels like a user space problem to me though? Like the user space tooling could build a tool that says these are the audits that you need. Here's the BTF for them. I'm not sure there's a kernel emitter. I think I'm adding.
So it's about right. It's about do we want to keep up with the kernel space whenever a new audit hook is added, right? So for example, if the perf people add a new audit hook, do you want this user space to keep up, right? And I feel that this is a chance that we will miss. There's information that is with the audit people, like this might not percolate down to the user space. So you need this sort of relation to happen in the association to happen in the kernel space. It's similar to the LSM hooks that we do for LSM, because technically, like you could implement all LSM hooks with fmod programs as well, with some minor sort of with things about integrity stuff, which is sometimes important, but may not be for all users who are not using integrity, because there's some side effects in LSM hooks.
Right, which is why we don't do LSM. We just hook the kprobe and fentry on my side. But
I think this is the advantage. As an advanced user, I can spend cycles building this, but as somebody who you want to build like a BPF program type for, you want to tell them, hey, this is where you can hook for mmap, and you get all the information about an mmap event. So, and also we need to connect this audit like stream of the information that is useful for audit, and like connect it to BPF, be it via perf or be it via something else, is the question that is up for debate. But I think like,
but it's definitely like I think the difference between us right here is like you're to me it feels like you're talking primarily about a user experience. Like how does a developer sort of understand what they should hook and on what kernel version, what functions they need to hook. And then from my side, on the kernel developer side, I sort of, and maybe in your opinion, too casual, and I just say, well, read the kernel source and figure it out, right?
Yeah, but this
like
is a leverage that a lot of the developers who want to use BPF don't have, right? The BPF community has grown much larger than the people who read kernel code and want to develop. So there is a user sort of persona that exists beyond your BPF trace user who wants to use BPF, right? So they don't want to use this like BPF trace or like slightly less advanced. They're more advanced user space developers, but they also don't necessarily want to dive deep into the kernel details, and that is one user persona that we see quite often, especially in the area that I work in. And the other part is that how do you connect when audit people, when audit maintainers, or when perf people, or somebody at some existing audit framework adds a new thing? How do you connect that information back in? Do we tell audit people that you need to document this project everywhere? Is there some user space project that is going to track every audit change in the kernel? Maybe that's an option.
So, I'll tell a joke, but I think you should probably watch the kernel mailing list.
Of course, like just try telling this to my security analysts, and then they will be like, "Sorry, that's not what I'm going to do."
Yeah, I know. I was just half joking, but also that's how you do it today, right? That's the point that I was trying to make.
I wanted also to emphasize one point that you sort of like didn't emphasize, I think. Like, so the part about like using the perf subsystem to actually audit a lot of interesting events, right? Like what what KP was saying about this ftrace. Can you go back like to the cflags slide, right? Like that's sort of subtle for someone who didn't run into this problem, and I did run, and it's extremely annoying. Like all the perf core code, right? Like the kernel/perf directory in the kernel, it essentially disables attaching to any function. So like you cannot do it through kprobes, through fentry, nothing. Like it just doesn't generate those first 5 bytes that are used by the kernel subsystem to attach not just BPF, but BPF as well. And so I think that's worth emphasizing, because we will probably need to solve this. Like it's impossible to like trace anything about the perf. So like perf event, open fails, nothing to do.
And honestly, like some of these places that I talked about don't have a function boundary association. So this is one thing I just like didn't mention here. So you don't have a function call in some of these places, especially for socket ops. You want to be somewhere in the middle of the function, because at the exit, there is a data structure that created and destroyed between the function that you really want to get your information from. So what do you do in that scenario? I think the tracing fx at entry points don't really like cover all of these use cases as well.
All right, so Song had the question about the task VMA iterator used for auditing mmap events, but he's sort of reconsidered. But I think it still might be useful, except that right now task VMA iterator iterates over all VMAs, while in this case you might want to iterate over like once, well, not even iterate at that point, but like you would want to look up the VMA for specific task ID. And we actually had a discussion about allowing to customize the task VMA. Yeah, Song.
So yeah, I think you use perf to do the mmap events. Basically, you want to know when a VMA is created.
Yeah.
And well, the task iterator right now is like to go through whatever like the task, and so maybe there's some combination of these two. Like if you have something VMA triggers and you want to mmap perf event triggers, you can use a modified version of that of the task VMA iterator to look at it, or maybe you actually want a hook or something that when there's a new VMA created, you want to trigger a BPF program to look at it.
So I think I actually love the task iterator concept for like, but the way I see where it fits in the whole thing is when you start a particular sort of auditing agent after certain point in the reboot, after you like certain point in the boot cycle, you want to backfill this information, like what is the memory mappings that exist currently in the system, or like what are the processes and what are their start times, so that I can track them better. This sort of falls in the iterator use case. But when you want like a point notification of when a new VMA mapping is created, the perf event mmap is nice. Now, I would really like if I could just get the perf event mmap with the C flags disabled somehow, or like we solve this mcount issue. Some of these things will go away. But I think Andrew alluded to the nice point there. Like you tell them, okay, you can use ftrace and fexit, right? And then people are like, okay, I will read the kernel source code. I've read all of this. And this is exactly what happened in my case as well. They read the kernel source code. They're like, this is the function that perf calls, perf event mmap. This is what I need to do to add the start boot time or the for the parent process. Let me do that. Kept failing, got frustrated. BPF doesn't work, right? And then you sort of, the whole developer experience starts falling through here. And this is why I think we need a dedicated API for those sort of uses.
So how about something like you have a perf event? If we have like say the task VMA iterator, so instead of you just let you specify what the it will let you specify the task and the starting address you want. So when you get a perf mmap to event, if that's enough, you just look at it. If that's not enough, you can use BPF to get the VMA, and you can look at the details with that.
I think that is helpful, like, but it is very, very on this particular use case, right? It is for the mmap use case. Then you have the kernel text loading, and then you have the BPF program loading and unloading, and you have other things that you would potentially want to audit. So I agree we might be able to conjure up a solution for the VMA mmap case based on the task VMA iterator. I don't see it in my head because it's also Friday evening, but I think like it is possible to build that. But then what about the other cases? Is what comes to my head.
Okay, so I'll ping you when I have a prototype for the helper, and I don't know whether it's going to be good for one use case or it's going to be good for a couple, but hopefully we get your feedback to make it, if it's useful, make it correct for you.
Thank you. This is awesome.
So Lawrence made a point about the K-probe, that K-probe actually has, well, relatively high overhead. And some people might not want that. So that was to the question, why not do the K-probes? Though like F-entry kind of eliminates that, so I don't know, kind of balances it out.
I mean, F-entry is nice, and I think chaining, the one pattern that solves your use case is chaining F-entry, and then if you can get the information at function boundaries, you can sort of build a larger context either with using the promise subsystem or like embedding data into task local storage. But there are some things that, like as Rafael was asking, and I thought I missed that question, but there are some things that are not available at function boundary, and then what do you do with that?
Right. Actually, to that point, like you were saying that like we can keep adding like new audit LSMs and all that stuff. I wonder like if the better or just like alternative, right, would be the bare trace points. Like those are trace points that are not exposed to the user space as, you know, like all those files in the tracefs, like with some overhead, and they're just attachable through raw trace point program types. So that might be another option, I guess, but it's still like you need to add new stuff to the kernel. So it's essentially like if we cannot make the perf events work, for example, right, we can add like equivalent raw trace points and like provide all the in-kernel data structures. And actually with the tracing programs, you have like direct memory reads like with all the type information. So with BTF, it's actually quite convenient to work with.
That would be cool. I was wondering like if this is one option that came in the past as well. I was wondering if we could somehow tag some trace points as audit worthy, and you solve this like attachment surface issue as well. Like you could just say that this is a BPF audit trace point, but at this point the value add is, if it is the same program type, the value add is just primarily like surface.
But regardless, I would encourage to start the discussion with the perf subsystem about like this C-flags problem. It's a problem, not just for your use case.
I have a quick question. KP, can you go to the audit slide?
Yes, this one.
No,
oh, sorry.
No. Yeah. Yes. So, so what's the concern for the major overhaul of audit?
I mean, the concern is that we will have to change audit. Like when you call an audit function, let's say I want to audit mmap. Audit mmap gets like just the FD of the audit log mmap is just the FD of the mmap thing. There's an audit mmap. The function I think is called audit mmap FD, if I remember correctly in the kernel. This is a statically inline function. Then this function calls audit context, which is like this huge structure of like a fixed. Alexei, you were saying something?
Yeah, I'm agreeing. It's just, yes, but like I think you're thinking about it as a LSM hook to intercept it as early as possible. So more or less like converging everything where like this audit map, etc. So what if we just add effectively 3 hooks to audit log start? And this audit log start is like getting this context, right? So it's creating the context, this init, etc. So I mean, like dumb it out. Like when the BPF is sort of enabled, like LSM, not quite a hook, but sort of keep all the audit stuff as is, and attach BPF to like audit log format. So
I like it. I think this is, I didn't consider this. So you're saying that the BPF attachment, rather than attaching to all this audit API calls, you sort of come to this end of the funnel.
One level lower, yes. Because there, like, it's a bit harder to, like, it will be, a bit harder to combine the states and know where exactly you are. So there may be like the need to get like function IP and the caller IP in some cases because of like static inline, and do some conversion from IP to a symbol. But the nice part about going into audit log format, like you will get all the arguments. You will see like all the audit stuff, they will prepare it relatively cheaply. Like and of course, like BPF side will just ignore the string that is passed there, the format string, but the formats will be there because that's the most valuable part, and it's already like prepared by all the audit infra for everything, more or less.
Yeah. I think this is a nice way. It may not solve all our issues, but it sort of opens up the audit subsystem to the BPF world, and which is what I like. I think
pretty much, yes. It's like connecting the two and like replacing the guts of audit, like removing all the SKB allocation and everything, and dummy it into just like abstract BPF specific context that is cheap, and programs will have access to all the arguments, and everything will be so much faster, no memory allocations, and running out of any context.
I actually like this idea. We should we'll spend some time prototyping this. It doesn't seem like that much work if you look at if you go into the audit log format. So yeah, this is a nice idea.
But of course, that's not one-off. Like what Andrei said, like yeah, totally makes sense. Like you do the perf stuff in parallel and everything else. Like everything that you mentioned, I think worth pursuing.
Yeah,
I'm just trying to adjust the cons for this explosive audit events from like a big issue to like it's probably not that big of a deal. That's the only thing I'm trying to say.
Nice. Yeah, I think what really happens is that you will have users who will have you will come up with all sorts of users, right? Like somebody needs to audit at the syscall boundary, so they will use syscall fentry fexit function. Somebody actually needs to get the same format as the audit logs because of some requirement. There are actually some weird requirements that come into this area that we really need the output format that audit has. I think this will play very nicely into that. And for us, it'll be very nice to get the perf event map to work. Like for me personally, like in this area. But yeah, we'll pursue that as well.
Daniel?
I also had a question regarding the LSM hooks. I mean, I haven't looked into it, but I'm not sure. Like for example, when you mentioned the module load, there's a missing name or something like where it just would require an extension. I would assume it's probably not that controversial to just extend it and just to try it out. And for the new LSM hooks, I mean, if they're not like in performance critical places, it's probably worth trying to pursue and maybe like to show the use case, like how you want to use it, like even if it would just be in a BPF self-test or so, but at least that would demonstrate the need for it, I would say. And I don't think there's much that people would argue against it, to be honest.
Okay. This is just like sort of not, this is sort of like resistance or inertia to change the LSM framework. We have put ourselves in our head, and maybe this is not really the case. So I think we should also give it a fair shot in some of the cases. Thanks, Daniel.
I would say so, yeah. And I mean, especially given you're using it in production and, you know, like this, it definitely makes sense to further extend it. I mean, if it can be proved that it's useful and needed, so why not?
Anyone has any other questions? If not, thank you, KP, for your talk. It was great. Seems like there was a lot of relevant discussion after that, so it's definitely interesting to people. So we have 10 more minutes till the next talk. We'll take a break and see you all in 10.5 minutes. Okay, it was 2 minutes to go. And while everyone reminisces about good old times when we can meet in person, Kyle, are you here? Can we do the sound check just to make sure everything's working?
Yep, sure thing. Mic check.
All right.
Oh yeah, sorry. It may look a little confusing because
I know, I figured it out.
yeah, render Kirti.
Oh, it's good that you guys are in the same room together. So unusual nowadays.
Yeah, it is nice to hang out together, and I think it's fun.
All right. Gonna give you presenters right status. Let's wait for another 20 seconds and start right on the clock. So just as an announcement, the next talk will be talking IPv6 to IPv4 without NAT. And yeah, I guess we can start. Go ahead.
Cool. All right. So my name is Kirti, and I have here Kyle and Alok.
Sorry, one sec. There is a pretty strong echo. So you don't need to share the screen. I uploaded the slides, and you can actually control them. You have now like the buttons at the bottom, so you can, you can use the pre-uploaded slides and just control them. So you can stop sharing the screen. Probably will solve the sound issue as well.
No, the sound was my fault. I'm sorry, I fixed that.
Okay.
But we would like to share the screen because there are some cool animations, but also we would like to do a real demo with the terminal.
All right. Sound good. Go ahead.
Yeah, echo should be solved. Go for it, Kirti.
All right. So Kyle, Alok, and I are going to present this. The topic of today is how we have a transition mechanism while moving over our enterprise to our IPv6. And we are doing that without using any NATing device. So how do we do that? So let's establish why we need to do this. So Netflix has a large ecosystem of microservices. We use hundreds of thousands of instances in Amazon AWS EC2. We have architected our network to use a flat IP space, so our networks don't have overlapping seeders, even though we've partitioned our network across multiple VPCs. Now, because of the way we've implemented our network, we are hitting scaling limits because of our consumption of IP addresses in AWS. And now many enterprises do have some alternatives to get rid of this kind of scaling limits by having different kinds of segmentation. But due to the way we've architected our network, for us, the only alternative is to move to IPv6. And when enterprises think of moving to IPv6, the first thing that comes up is why don't we dual stack all devices with a v4 and v6 server? So in the last slide, I spoke about scaling limits. The reason dual stack doesn't help us is because we will reach those scaling limits even faster when we dual stack. So obviously that's something we don't want to do. And also as network engineers, we want to change the network without application engineers noticing it and it being very seamless. So the question is now, how do we move from IPv4 to IPv6 transparently? And here is a graph that shows while we were developing this transition mechanism, how the network flows within Netflix have been moving to predominantly IPv6. Our goal here is to make this entire graph turn red by having all IPv6 flows within Netflix. So when we move to v4 to v6, what is the state of the art to implement this mechanism? You all guessed it, it's network address translation. So for the network address translation will translate IPv4 to IPv6. There are some state-of-the-art mechanisms to use NAT. We want a simple NAT here, just convert the v4 to v6. There are software modules to do this, like Tega. Then there's also, of course, you can buy a beefy box where you can send out your network connections out of the box, out of AWS, gets into this dedicated hardware, and then comes out with a v6 address. Of course, all these mechanisms have the singular problem, which is like per packet processing. And apart from the latency and additional hardware, this per packet processing can be tedious. So can we do any better? So that's where TSA comes in. And Kyle?
Thanks to your team. Yeah, if we know we want IPv6 only as our solution, how are we going to get there? TSA is the solution that we've come up with. TSA is short for the Titus syscall agent. And to define that, we're going to define Titus. Titus is Netflix's multi-tenant container platform. It's kind of like Kubernetes, where we control different containers on an individual host, and we run lots of them on a host. Shared kernel, though. The TSA, the Titus syscall agent, protects our shared host because we don't really trust what other workloads are running, but also enables new capabilities. For example, TSA enables the perf command. So people in their containers can run perf safely because TSA is intercepting that perf syscall, mutating it to make sure it's only capturing what's in their own container, and they can't accidentally or on purpose try to get performance counters from some other process. Same with the BPF syscall. Perf uses the BPF syscall anyway. But that's not what we're going to talk about today. We're going to talk about the TSA intercepting the connect syscall because we're talking about networking today. But it's just one example of the power of being able to intercept and manipulate syscalls on a host in a shared environment. But in order to talk about how it does that, we have to look at some different examples of how we intercept syscalls, because there's a couple different ways. One way you might think to do this is with LD preload. This is kind of a non-starter for us because we don't really control the workload. It doesn't work with static binaries. It's kind of out there. Kernel modules is another approach. You could certainly just write your kernel module and do anything you want, but as Linux Plumbers knows, kernel modules, they can be a little hard to write and a little hard to iterate on, and you don't want to crash the whole kernel just because something goes wrong with one individual container. It'd be nice if we had some protection. There's a couple other methods, but the method we're going to talk about today is SecComp, secure computing, which isn't, at first glance, you don't think of it as a way to manipulate syscalls. It's mostly, it's like a firewall for syscalls. You do allow or deny, but there's a couple other things you can do. Starting in 2017, there's a new method, a new thing you can do, which is to notify. So not just allow, not just deny, but a third option, notify, which sends that syscall on to another process listening on a socket to do something else. And then, most recently in 2020, thanks to Sargon, who's a team member of ours, added and upstreamed the ability for the SecComp notifier to add a file descriptor in its response. So now we're really talking. Now we can intercept the syscall, do something, and then reply back with a file descriptor with more stuff. And that's going to be the secret sauce that powers Connect, but it also powers perf and BPF. Let's look at some complex sequence diagrams to really get a feel for what's actually happening beneath the hood, and then we'll do a demo to show off this program. On the leftmost side, you see Titus. That's our orchestration thing. That's the thing that's actually launching these containers. And because it's launching the containers, it's got the hook. It can install the SecComp policy as we need. And even before TSA, we were installing SecComp policies for security reasons. But with TSA now, we have that third option, which is to continue with the notify with adding FD. So when Titus sets up the container, it sets up that special SecComp policy. It gets back the notification FD that it needs to respond to with the incoming syscalls, specifically the ones that we're controlling, which are connect and perf and BPF. It, through SCM writes, sends that notification file descriptor onto TSA, which is a separate process running per container, so they're isolated, but they're set up to intercept these syscalls and operate on them on their behalf. When the container is actually launched, and it actually makes an actual syscall, that syscall does go to the kernel like normal, but because of the special SecComp policy, it gets sent over to TSA to be handled. TSA can do a couple of things. It can just send it right back and say, this is good to go, but it can also get a chance to make that syscall on the server's behalf, so on the container's behalf, and then return with a continue or an add FD optionally. And that's the magic that allows us to take a syscall, do something different. return a file descriptor back to the container for it to continue to do whatever it needs to do. But how does this all work in the context of networking? Because we're just talking about syscalls and file descriptors. We haven't really talked about like IP addresses or anything. So how does this magical thing interact with actual v4 and v6 servers?
Cool. Thanks, Kyle. So on the left-hand side, we have a IPv6 container having a v6 address. So that's a IPv6 client. Now, as Kyle was talking about, so we've added a seccomp filter. So this container will be able to send all its system calls or some system calls to TSA. So when the IPv6 client wants to talk to an IPv6 server, which is like the happy path we're going to talk about here, it issues the connect call. The connect call is going to be intercepted by TSA because of the seccomp filter. Now, TSA checks if it's a valid v6 destination. And in this case, it knows that the v6 client can talk to the v6 server by itself, and it gets out of the way, returns the response. And from then on, the IPv6 client is talking to the v6 server, and TSA is no longer in the picture. Now, let's see what happens when a IPv6 client wants to talk to an IPv4 server. And this is without TSA. So without TSA, there's no interception of any kind. The v6 client makes the connect system call. The kernel responds saying that it cannot reach the host. And connection fails, of course. So how can TSA come to the rescue here? So with TSA, again, we intercept that connect system call, which was supposed to go to the kernel earlier. And now the TSA figures out, hey, can I reach this v4 server from the container's namespace? It cannot. And then what it does is it issues the connect call on behalf of the container. And the way it does that is in another namespace, we have another v4 address. It leverages that to connect to the v4 server. So the result of this connect system call, as you guys know, is a file descriptor. So what it does next is what Kyle spoke about earlier, where Sargon added that facility to change or mutate the file descriptor. So it replaces the file descriptor, the original file descriptor, with this new file descriptor that it got from its own connect system call. And once it does that, right, the TSA gets out of the way. And the communication between the v6 client and the v4 server is as if there was no TSA. So there's no per packet processing. There's a once in the lifetime of the connection, we do this mutation of the FD. And from then on, the packets between the client and the server just go uninhibited. So that's the value add here. So that's all the talk of how this interaction works in TSA. Now over to Alok to do a demo for us. Look.
Thanks, Kirti. So let's move on to the demo. So we'll be demoing how TSA is able to connect to a v6 only server using an IPv6 address. So we would be demonstrating how TSA helps your service to connect to a v4 only destination. So to start with, let's say you've migrated your application to IPv6 only mode, and you're just exploring how the connectivity works to its dependencies. So to start off with, we have this container that's running only IPv6. So we can confirm that using the current network configuration. So we see that at 0, it only has IPv6 address assigned. As it's obvious, curl, like running a connect call to a v6 only server should work fine. So we'll just use curl to show that connections to v6 only destinations work as expected. So as we see, once we run this curl command, it's able to connect to this website using the v6 mode. So now let's see if you try to connect to a v4 only server from this container, what happens. So if we run the curl command using the -4 option, so as Kirti mentioned, connecting to a v4 only server from a v6 only server would return an error, which is network is unreachable. So as you can see, what could happen is as you move your applications to V6, there could be certain dependencies that have not yet migrated to a V6 world, and your connections to those services might start failing. So next, let's see how TSA helps us in this regard. So now I'm switching over to a container that's running with TSA to help connections go to the V6 only server. So again, to confirm that we're just running in V6 mode. So we run an ifconfig on net 0. We see that we only have a V6 address here. Then, and since we are running only in V6 only mode, curl command to a V6 address should just work fine. So now when we connect to a V6 only destination, we see that this works as expected. So now just to confirm that we would be able to connect to a V4 only service using TSA, I would just have some other windows open to just show that connectivity works via TSA. So I'll just start a strace or a trace call on the TSA process that's running on the container host. Again, I'll also be starting a log on the TSA service itself. And as Kirti mentioned, TSA makes a connect to a V4 only service via a V4 address. So what we do is we have like a V4 only network space created for the TSA to run in. So this is the particular V4 only network namespace. So we have a interface aptly named as transit, which is actually used to transit to a V4 only service. So just to confirm things work fine, I'll start a TCP dump on port 80 on the interface transit. So let's see what happens when we connect to a V4 only server from this V6 server. I'll run a strace on the curl command to the V4 only server. So here we see that we are successfully able to connect to a V6 only, V4 only destination. We did make a connection to this V4 address on port 80. When we show a strace on the process TSA, we see that TSA actually intercepted the connect call from the container and made a connect to the V4 only destination. And just for some extra confirmations, this is a sequence of how TSA intercepts syscalls from the container host. So we see that TSA got a connect call from a process curl with these parameters. TSA then checks if a V4 route exists within the container's network namespace. So it figures out that there's no route to connect to that destination. It then, on behalf of the workload, it makes a connect call. And then using the seccom BPF syscall, it mutates the original connect FD with this new FD, which was used to make a connect to the V4 only server. Again, TCP dump is another confirmation that we were actually able to make a connect to this particular destination over V4. So that's all for the demo. I'll give this back to Kirti for the rest of the presentation.
Cool. Thanks, Alok. So, all right, so that was the demo of how TSA is the transition mechanism, so that we do the translation once in the lifetime of the connection. And once the file descriptors are mutated, the TSA is out of the way, and the packets go uninhibited. So TSA is not interacting with anything after the initial connection establishment. All right, so in terms of performance, we don't have a lot of performance numbers. We're still working on getting these numbers. So On the left-hand side, I have like a happy path. The happy path is basically when we're trying to connect from a V6 client to a V6 server. But what's important is we are intercepting every connect call. So there is some amount of processing that TSA does. And if you can see, the orange bar is where TSA is involved. So there is some involvement of TSA right now with single threaded. So there's some performance impact. We have to work on it. On the right-hand side is the non-happy path, or rather where the TSA is actually functioning. It's swapping the file descriptors. And I'm just running curl in a loop. And we see that there is performance impact in that for about 1,000 curls, there is about 6 seconds of impact. For each connect call, we do, of course, do a bunch of other system calls just to enable connect to work, right? So there is impact. We're still working on the optimization. So the takeaway here from performance is, of course, there's an expected latency impact in the connection establishment, but we expect that impact to kind of get amortized over the lifetime of the connection because of the number of packet exchanges, and we don't do any per packet interactions. And internally, of course, we have a tool to also chart the different syscalls we're intercepting to get this whole transition mechanism in effect. So apart from the connect system call, we do intercept send message calls also. And of course, BPF and perf event calls are also being intercepted for various functions of the TSA within Netflix infrastructure. And now talking about where we're going with this in the future, when we were implementing the TSA, we came across a couple of fixes that need to be done within the kernel as part of maybe the extension of the addFT support. And Alok has been taking this up with the kernel folks. And eventually in Netflix, we'll be using the transition mechanism by default in production as we migrate towards V6. And in the long term, the company will be IPv6 mostly everywhere. But when we're talking to some third-party services, which are probably IPv4 only, TSA will get invoked. And all this will be seamless without the knowledge of the application engineer. So TSA will also continue to be used for features like perf and BPF tools, as Kyle was talking about. Yeah, so that's the wrap. So that's the presentation, and we're ready to take questions.
We can do questions, and we also have a demo open still if you are curious or if you want a command from the audience for us to run for you. We'll do our best. But as mentioned in the chat, this is an incomplete implementation. It doesn't support everything you could possibly do with TCP and IPv4, mostly because we consider this a transition mechanism. We consider it to be like a backup. It's an auxiliary outbound IPv4 only for those things that need to connect to v4 who haven't migrated to v6 yet. So it's kind of solving that chicken and egg problem where we want to be on IPv6 only, but we realize that there's going to be some things that aren't ready to be IPv6. So this is that transition mechanism in action.
All right, Daniel, let's go, and then we can go back to the chat questions as well.
Okay, so thanks a lot for the interesting work. I have 2 questions. So question 1 is like, given you're giving the application an IPv6 socket, and your goal is to not modify applications that exist to ease the transition, have you seen or experienced any breakages? For example, when they use set sock-up, get sock-up that are IPv4 specific, but they have no support in v6. So first question is, how have you seen anything like that, and how do you handle this?
Alok, would you like to? He's probably seen the most breakage from real-world applications with ePOL.
Sure. So we did. So we did see an issue where certain applications are, like once they create a socket, they actually save the socket in a ePOL structure before actually making the connect call. So once we get this connect call and we get the socket FD and we try to mutate it, we are actually mutating it with a new file descriptor, and the original file descriptor, which the application added to the ePOL, is lost. So what we had to do in turn is, before mutating the file descriptor, we had to actually go and figure out if the current socket which we are intercepting is part of any ePOL structures in the original application. So that's the additional part that we do within the TSA, so that happens there. Ideally, a good fix would be to do that within the kernel, like walk through all the file descriptors that are added to an epoll structure by an original process and do a replacement there. But currently, as a stopgap solution, we do this within the TSA. The errors mainly that we ran into were like once we mutated the file descriptor, the original application used to report that it couldn't find the epoll monitored file descriptor. I think that's the main issues that we've faced right now, like using TSA.
Yeah, luckily, we only need to build a solution for Netflix, so we don't have to support every application under the sun, and we only have to support the applications that are actually going to use this thing, and that means that it's Netflix's stacks basically. Yeah. That's how we're able to get away with such a thing.
Okay, and my second question would be, so I would assume the TSA agent, is it running in a separate network namespace or in the same as a process? I would assume a separate one, right?
That's correct, yeah.
So if it allocates a socket, the socket would reside in the TSA namespace, and you hand the socket over into the target container namespace, right?
Yep.
Which would also have the implication that you couldn't see any traffic that was emitted from the application itself. So like the troubleshooting might be more tricky. So how do you handle that?
Yeah, absolutely. In the demo, you saw the TCP dump that was running from the shared namespace, though, not from the containers namespace. It's true that when you run things like TCP dump, you won't see the packets because they don't belong to your network namespace. Yep, that's absolutely a thing we think about. We have other additional network observability tools at Netflix that, because we control them, we can augment them to be like TSA aware. But for the most part, we're kind of sucking it up and just thinking to ourselves, this is, because it's a backup transition mechanism, we don't expect applications to use this as their like primary connectivity. We're hoping that we can get away with kind of a less great troubleshooting experience. And be okay with it. Yeah. The TSA logs are pretty good. We made sure, because we're debugging our own stuff, that the TSA logs are very clear about what's connecting to what and why it didn't work. So those help a lot. But when it comes down to it, yeah, a person who's doing hardcore debugging is going to need to like TCP dump in two places.
There was a question on whether we support UDP only or TCP only.
Hold on, maybe the moderator might give us.
Yeah, so I think like the first one was the question from Toki about the performance comparison to BPF-based NAT64 solution. Toki, if you want to expand.
Yeah, we haven't done that performance thing yet. I sure would like to. For one thing, we do know that when it comes down to it, it's hard to beat a non-translated IP. This whole talk is without NAT. These packets are not being translated. So if you're just measuring raw like iPerf, where there's just a connect, and then once you're there, it's just read and write, the TSA is going to be hard to beat. Now, that being said, the latency for transitioning these namespaces and doing the connect and all this like FD stuff, yeah, that's kind of sucky. So the latency is gonna hurt. Kirti had some numbers on the previous slide, but we don't have any great numbers on like throughput in comparison to the BPF NAT64 thing. Yeah, it's future work for
us. So Dave has a bunch of remarks, Dave Taylor, about the UDP, TCP, and stuff like that. Dave, do you want to ask it in voice?
Can you guys hear me?
Clearly.
Yeah.
Yeah. Yeah. So my question was, since you can use Connect on UDP, I imagine that your solution could actually work with connected UDP if the application does that. Have you tried that? Did you make it work with Connect for both UDP and TCP, or have you only tried the Connect with the TCP path?
Yeah, I think predominantly it's only been TCP. And the other thing, of course, in our favor is that we in Netflix we are predominantly TCP, but we do intercept send message too. So that's with UDP. So the function of it's kind of we try to be transparent whether we're handling UDP or TCP, but we do handle TCP predominantly.
Yeah, part of the reason that I ask is, of course, that like Quick is going to be doing the replacement for TCP is over the top of UDP, and if you do connected UDP, then I imagine that you could have an upgrade path to Quick fairly naturally. So
that's right. Yes, we're aware of that. Yeah.
One unfortunate side effect of how we've designed this is that Quick using UDP, we are going to have to intercept every send message. So unlike the connect TCP use case, where once we do the connect, TSA is out of the picture, performance is line rate. With UDP, we have to intercept send message and receive message, and it's the performance is not going to be great on UDP. We're hoping that any performance sensitive UDP application is not going to use TSA and instead switch to either V6 only mode if they can, or just do traditional VStack, and that we'll just have to live with that.
Okay, thank you.
It seems there is like a bunch of other remarks about like various different shortcomings and downsides to this approach. So I don't know if anyone from like networking folks would like to summarize that. That would be great. Or you guys can, you read the chat like you might want to.
I can see. Yeah, like we are extremely aware of how it's not that limiting, but like how not comprehensive this solution is. But what we do like is the fact that this can be done, in theory without changing people's applications. And the big idea here is that we don't have to do a dual stack for everybody. So now we have two IPs per container, and that we can't afford that. And yeah, we don't really expect people to use this transition mechanism for fancy stuff like handing off the quick stuff, the zero downtime stuff. This is only for outbound. This is only for clients that need to connect to like GitHub v4, for who knows what reasons. Because we control most of our applications at Netflix, if there's somebody who's not a V6 ready, we can just ask them to be V6 ready so that we don't have to use this weird slow path, and they can stay on V6 and be happy. And then I'm looking forward to the day that we can turn off TSA or turn off the network configuration of TSA, where we can just do V6 only. We don't have to worry about this at all because we just live in that world. But to get there, we need this intermediate step. But yeah, it's definitely not a complete solution.
Do you have any estimates when you will be like IPv6 only? Like, do you have any plans?
Yeah,
just curious.
From the progression of the slide that you saw earlier, we've been making good strides towards that in terms of progress. And there are various asks even from our SDN that AWS provides. So again, the ballpark estimate would be a couple of years, a few years from now, would be V6 only.
Yeah, that high bar chart, the V6, that chart you saw with the V6 flows, most of that came from being dual stack, not via TSA, I'm sad to say. Maybe in this next year, the majority of V6 flows will happen on V6 only containers. But most of the progress that we've made on V6 today is because of dual stack. It's just at Netflix, we can't sustain dual stack forever. We just can't give away an IPv4 for every single container and an IPv6.
Rodrigo, do you want to ask this question? So Rodrigo is wondering like about if you replace the FD at the socket syscall rather than connect, would it stay out of the way for UDP packets that use connect and send instead of send to? No idea what that means. I'm not networking person.
Sure. So today we don't intercept socket, the socket system call itself, but that's an interesting idea. We can definitely try it out. Yeah.
So we would still have to like intercept the connect call again so that the connection could be made from the v4 only network namespace. So yeah, we would have to track socket FDs across system calls to do that. So it would be create a socket in the v4 namespace, track it down till its next connect call, so that again the connection could be made from the v4 namespace.
So right now, yeah, as Alok was saying, the TSA is stateless for obvious reasons, but yeah, if we do that, if we do intercept a socket for whatever reason, we'll have to maintain some state.
Dave, do you want to ask some more questions?
Sorry, I was in the middle of typing. I think Rodrigo's suggestion about hooking stuff at the sockets layer, at the socket call, I mean, is I think what is most consistent with the bump on the host RFC. So probably definitely something worth looking at. The question that I was going to ask is, on your bar chart, right, your trajectory just showed, if I remember right, just from February to August, you'd gone from 0% IPv6 to 25% IPv6, if I remember the top part of the graph, right? So my question is, at this trajectory, do you have any guesses right now as to whether you think you can pass 50%, or do you think you'll need to like change applications or do something else major to pass the 50% line? Was my question.
Yeah, to get past that 50% line, we're gonna have to do probably two things. We're gonna have to push really hard on our biggest applications who have lots of containers, which again may not necessarily correspond to the biggest applications. They're just the most prolific ones, batch jobs, things that are like launching lots and lots of stuff. We're gonna have to push really hard on them to adopt that. And luckily we have good relationships. Kind of unspoken behind the scenes here is we're actually on different teams. And one thing I'm kind of proud to work at Netflix where we don't like Conway's law isn't so strong. So like we can like make friends and establish relationships and like convince the other teams that this is good for Netflix and like it's necessary for us to survive in the long term. Therefore, convince them to move their application to be on this network transition mode. Granted, it's weird, but it's going to help us survive as we transition to v6 only. So we'll have to really ask and kind of like get our biggest users on Titus to have faith that we'll take care of them from a network perspective if we move to this kind of high performance IPv6 only scalability mode. So handling those biggest applications. And then the second thing is we as we ask them to move over, we need to make it really, really good. So we need to make it we need to increase the transparency to make it so that it's very clear when something's not working and it's v4. We need like the insight tools that we talked about. So that give and take to get us to past 50%, it's going to take a lot of convincing our fellow team members and getting to actually use this thing. That's what I think. I think it's a people problem at that point.
I just want to say, cool. I love the fact that you've got from 0 to 25% in like 6 months or something. Awesome trajectory. Please, keep it up. Let's see if we can keep moving that. I think the world will love that. So, thanks so much for presenting this. So,
yeah, thank you. So keep in mind that these are internal Netflix numbers.
I get that. Right.
Okay. And part of that is the power of a platform. So Titus is really the key here. Like we have a platform where we have this shim where we can kind of influence the defaults and the recommendations and that sort of thing. That's the real power of having a shared platform that users use. Contrast to like the traditional approach where everyone has like their own VM and they can kind of do whatever they want. We don't really have a hook. We can't like get in there and say, hey, here's the best practices. Here's what's best for Netflix at the network layer, that kind of stuff. But it's thanks to Titus that we can kind of inject these opinionated defaults and opinionated like things that can help push Netflix, the org, forward. So that's the real magic, is having a shared platform.
I guess my last suggestion is, I think this is the sort of presentation and the work that you guys are doing is the sort of thing that I think that the V6 Ops Working Group and the IETF would love to see presentations like that. So if somebody from Netflix is interested in doing that, I think this is the sort of thing that people love to see, these sorts of discussions, because Netflix is probably not the only organization in the world that's running into similar problems, right? And so being able to share learnings like this is exactly what the purpose of that working group is. And so we've seen a number of other presentations for similar but not the same types of problems and stuff. And so if you'd love to do that, I know the industry would love to hear more about this. So again, nice presentation. Thank you.
Okay, cool. Yeah, we'll keep that in mind, and maybe just I'll look up that working group and see if we can get a slot and share. Yeah, this is definitely an alternative approach to what a traditional enterprise might do with, of course, dual stack. Like, is there another way? This is definitely a weird way.
Eric also had a word of caution about this solution avoiding network bandwidth management, NetNS-based bandwidth management, and all that stuff. Eric, if you want to expand on that thought, you have the mic, so go ahead.
Well, no, that was just a general remark about bond weight management, either NetNS or C group based. So that evasion might be something to consider in the future if you want to properly attribute bond weight to the container, which really owns this FD, this socket.
That's a great point. We do take, in the normal networking modes, we do take a lot of work to make sure that containers are fair and that they can't abuse and take up too much of the bandwidth and stuff. And you're totally right that this transition network mode, in the very nature of it being shared, means that it's shared and potentially opens it up for abuse. Yeah, definitely point taken. We must protect it in some way to make sure that no bad actor can consume too much of that transit bandwidth.
Yeah, but overall, I want to thank you for this nice idea. It's nice.
Thank you.
Just for the sake of connecting this to BPF in some way, right? Like I'll put my BPF hat on, and I'm just wondering, like, if you wanted to achieve the same with BPF, right? Like, what's still missing from this, right? So like the sequence diagram, it's pretty involved, right? Like you transition between kernel and user space and all that stuff. Like if you wanted to either simplify or improve the performance of both, right? And like maybe even some of those limitations could be avoided if you do some more in-kernel magic, right, from the BPF side. Like, do you think like there is anything that BPF can provide to make this more universal, I guess?
Yeah, it's a great question. The BPF NAT64 implementation that I've seen,
I mean, possibly. I think the big deal, I think, is to actually have the add-FD support. So of course you can intercept the connect system call. You can try. So what we're trying to do is read another process's address space, right? So we're reading that and trying to figure out where it needs to connect to, make a route check, and then eventually in the success path we want to add that, call the add-FD on the seccom system call. I think enabling all that under the hood. Yeah.
So you can think about this the other way, right? Like right now you're reading user space's memory, like just to get like the configuration, right? Like with the way that BPF normally works is actually you have in-kernel data structure that's exposed to user space, and user space actually maintains that and updates it and all that stuff, right? So both BPF side can read it. So in this case, like if you have some like lookup tables, you can actually like populate them in kernels, like through BPF maps, right? And then like all the logic will stay inside the kernel in your custom BPF program. So again, I'm not a networking person. I'm just saying that, think about like how would you do it like with BPF. If you're not very familiar with BPF, then I guess it's just a good investment just to learn a little bit about that. Just shameless plug about BPF here. So.
No, totally. I think that's one approach. I mean, we are slightly familiar with BPF, but it's not an approach we examined closely because we had been running with the seccomp add-FD. Sargon worked on the team. It's been a strategy to go in this direction, but definitely we should explore if this can be achieved from BPF. We have other initiatives that use BPF programs to do socket lookups within the team and to do network interception. So yeah, it's something that we can definitely explore. Yes.
Sounds good. So Dave Taylor was telling like more specifics about this IETF group. Please check that in the chat. I'm not going to repeat all that. Sorry.
Yes, I think the other thing is, of course, there's a team within Netflix that is driving the IPv6 migration. We're also going to present the findings, our migration approaches and direction in reinvent this year. So definitely there is momentum in trying to showcase our efforts to move the entire enterprise to V6 completely, and share it with the industry. Yes.
All right. Anyone wants to ask anything else? We have 7 minutes to go till the next talk, so we have a little bit of time. If there is any interest. Okay, I'll assume not. So that will conclude this presentation. Thank you very much. It was great, and judging by the amount of generated discussion in chat and with questions, a lot of people were interested. So thank you very much for contributing this presentation. And we'll take a 5-minute break till the next presentation, 6. And please come back soon. Thank you. All right, Guillaume, let's do the sound check as well.
Hi, do you hear me?
Yep. Don't see you yet.
Okay. Is the webcam working now?
Well, yeah, now it does.
Okay.
All right, I think we can get started, so please go ahead.
Okay, so yeah, in this talk I'm going to describe the problems we have in the Linux kernel regarding the way we handle the toss field in IP packets. So the main problem we have is that we handle the toss in somewhat inconsistent ways. And because of that, regressions are introduced every now and then. Some corner cases are still needing to be fixed. And it happens that I think it was 6 months or 9 months ago, some risky patches were proposed upstream to extend the functionalities. So it would be good to fix everything before we get more risky patches. So first, let's have a short look about the history of this field. It was defined first in RFC 791 as a 3-bits field. That's the T bits here. So that's the original IPv4 RFC. And then it was extended and modified again with incompatible interpretation. For example, in RFC 1122, it was extended to a 5-bits field. And afterwards, the lower order bit was finally reserved. And with the introduction of the SCP, another lower order bit was reserved. And those 2 bits were finally repurposed for explicit congestion notification. In IPv6, we also have conflicting interpretation. The original specification defined the 4-bits field. And again, it was extended this time to 8 bits. And finally, the SCP reserved the last 2 bits, which were finally repurposed for ECN. So now we have a stable interpretation, like in the last 20 years, the definition of the toss field hasn't changed. And the nice thing is that it's the same now for IPv4 and IPv6. However, the networking stack was implemented before ECN and the SCP. So with all those conflicting interpretation, of course, we have a pretty messy implementation. So for example, in the IPv4 code, we ignore the ECN bits when we try to match the toss. But the IPv6 code doesn't ignore them. So that means that depending on the ECN values, IPv6 might treat packets differently, even though the toss is the same, but because of the difference in ECN bits. For the higher order bits, IPv4 ignores them, well, most of the time, because some parts of the code takes them into account. IPv6 is more consistent. It always takes all the bits into account when it matches the toss. And another effect of this, how to say, messy implementation is that we can accept toss values, for example, with IP root or IP rules that cannot actually match any packet. I will give some examples later. So the reason for all those different interpretation is mainly because of the use of two different masks in the IPv4 code. There is first RTTOS, which is used very widely in the IPv4 code base. So this mask clears the high order bits, and it also clears one of the ECN bits, but only one of them. However, most of the routing code will apply another mask, which will clear both ECN bits. So RTTOS actually doesn't really make any sense, because every time we do a route lookup, even if the caller masks the TOS with the RTTOS macro, the routing code will mask the TOS again to clear the ECN bits. In IPv6, the situation is very different. We normally don't mask the TOS at all, but probably because of copy-pasting code, there are some occurrence of this RTTOS macro that spreads into the IPv6 code base, where it just doesn't make any sense. So there are user-visible consequences. For example, in the past, we had bugs where RP route get wouldn't return the proper route. We would have different, a real packet would take a different route than what IP route get would return. We had some regression in VXLAN due to the way we handled the TOS, because some fixes changed the mask of the TOS in the VXLAN code. We had problem with source address selection, and we had more problem, for example, with the early DMX, I think. And so these problems have been solved, but yeah, there are the more fundamental problems that remains. For example, the inconsistent handling of the high order DSCP bits, especially in IPv4. Of course, we have a different behavior between IPv4 and IPv6, and we have the problem of risky patches that have been posted. And yeah, sometimes maybe we will mistakenly apply that kind of thing. So just some examples of the practical problems or surprising behaviors that we can encounter. Let's try to use IP route and define a route with TOS1. This is accepted, but if we try to route a packet with TOS1, the route will not be found. Because TOS1 actually sets an ECN bit, and as I said, the ECN bits are cleared before doing the TOS comparison. So yeah, let's try with TOS4. This is a bit that is defined for in every RFC, so no matter the interpretation of the TOS, it's a valid TOS. So that works. If we have a packet with TOS4, it will take this route, no problem. Something that might surprise some users is that this route will also match packets with TOS E4 because E4 will be the E part of E4 will be masked by the IPv4 routing code because that's the high order DSCP bits. So yeah, we can match packets with TOS E4 by using just TOS4. But if we try to explicitly match TOS E4, well, actually, we won't match it at all. Again, because of the mask that is applied before routing IPv4 packets. And with IP rules, we have slightly different behaviors. If we try to use TOS1, this time the command is rejected. But if we try with TOS2, the command is accepted, even though it's another ECN bit. And we have the same problem as with the IP route with TOS1. That is, no packet will actually match this rule because of the way IPv4 clears the ECN bits before doing the lookup. With TOS4, we have the exact same behavior as we had with IP route. And if we try to set the high order bits, the command is rejected. With IPv6, we have yet different behavior. IP route with IPv6 just ignores the TOS parameter. So yeah, at least it's consistent. We can provide whatever TOS we want. It's never applied. With IP rule, the TOS is accepted, of course, and we can use any value, even ECN bits if we want. So I don't know if there's a use case for matching the ECN bits with IP rule, but it's probably dangerous as a network administrator who doesn't know much about TOS and DSCP and ECN might try to match or to use TOS1 and have some special handling for it, and finally mess or break ECN without even realizing. So what can we do? Yeah, first we can fix the obvious bugs, like the use of RTTOS in IPv6, and fix the few places in the IPv4 stack that doesn't match the ECN bits before matching the TOS. We can also probably remove most of the RTTOS calls because, as I said earlier, we generally will apply a stricter mask before doing the route lookup. And there's the long-term fixes or things we could do to address the fundamental problems. So, and this is where this is why I started with this talk. Actually, it would be good if we could define the behavior that we expect from the TOS. Like with the previous IP route and IP rule commands, should we configure them, consider them as established behaviors that we don't want to change, or is that bugs, or are some of them bugs that we need to fix? And once we settle on precise interpretation of the TOS field for the Linux kernel, then we can rework some internal code to minimize the chance of introducing more regressions in the future. I could think of two possible options for this. One would be to define a DSCP type. So, for example, it would ensure that the ECN bits have been masked, and sparse could warn when it's the DSCP is is mixed, for example, with unsigned integers. Another option, a bit more involved, is to change the way or to extend the way we configure the TOS in IP route and IP rules and also modules that happen to use the TOS. So we could extend the TOS configuration by adding a mask. So instead of having an implicit mask for IPv4 and another one for IPv6, and actually having even different implicit masks, depending on which part of the IPv4 stack we are running. We would, in the route or in the IP rule, have the possibility to define which mask to apply before comparing the TOS. Potentially, we could allow the ECN bits in the mask, so that we would keep the current IPv6 behavior. So in practice, option 1 would look like this: a new DSCP type so that sparse could warn about it when it's compared or assigned to other different types, and a couple of helper functions to convert between plain integer to DSCP and the other way around. And of course, when we take an integer and convert to DSCP, we would apply the mask. There are a few drawbacks to this approach. The first is all the code churn, because TOS is really used in many, many places. So, for example, it's not only about core routing, but it's also all sorts of tunnels, VRFs, some networking drivers, BPF helpers, etc. Some higher level protocols like SCTP. Also, sparse warnings can go unnoticed, and we have many files in the networking tree that are not sparse clean. Maybe patchwork could help by flagging patches that add sparse warnings, but I'm not sure if we have a policy about that. That also means that we wouldn't have much flexibility. So we would have to define what is the mask that we want to apply, and that would be set in stone. So yeah, do we want to allow the full DSCP range, or do we want to keep the current behavior, which is to mask the high order DSCP bits? And what about IPv6? IPv6 currently doesn't mask anything. So if we don't want to change the behavior of IPv6, we couldn't use the DSCP type for it. That might not be a problem, but that also means that for code that is supposed to handle both IPv4 and IPv6, we couldn't use the DSCP type. So there's the option 2, which is more flexible. So again, we could define a new type for it, which would contain the TOS value and the TOS mask. And then we could extend the different interfaces to the configuration. For example, here with IP rule, we could set the TOS value and then the TOS mask. So yeah, with this, we could allow using the whole DSCP range for users who want it. If we want to keep the original behavior where the high order bits are cleared by default, we could use a default value that does this. So that, yeah, quite a lot of flexibility. And we could use different masks for IPv4 and IPv6 to keep the same behavior by default. There are a few drawbacks to this approach too. First, it's a bit more involved than the option 1, especially because we have to modify code deep into how fib lookups are done. So it's a little bit more risky. And that would introduce some interesting problems. Like now, for example, one packet could match several routes, and there wouldn't be a route that is more specific than the other. So, for example, if we have this toss and a packet with toss 50, which route should we return? So, yeah, we could use some arbitrary rules, or we could say that, okay, the first match wins, or something like that. But yeah, it's not as natural as longest prefix match or something like this. Also, we have the problem of wildcards. For example, if we have a user that sets mask 0, but with a toss value of 0 and a mask that is not 0, is that a wildcard or not? And what about the default mask? If it's 0 with the default mask, normally it should be wildcard because that's the way it works. But on the other hand, it would make sense to actually allow a toss of 0 and a different, a non-zero mask to work. And finally, is it worth it? Are people really going to use a toss with a non-default mask? Yeah, it would be annoying to add this kind of flexibility and complexify the code if it's not used by anyone. So, conclusion, ideally we would have full support for IPv4 and also IPv6, and we wouldn't break ECN because of invalid configuration of the toss, and have consistent behavior across IPv4 and IPv6. Probably we'll never get there because of established behaviors. So what we can do is fix the obvious bugs that I presented at the beginning of the talk, removing the macros that, at least the usage of macros that don't really make sense, like RTTOS, so that people stop copy pasting them. And finally, discuss and settle on how we really want the TOS to work in the long term, so that we can finally address the root of the problem and rework the code, either with option 1 and using sparse to flag problems, or using the toss mask as option 2, or if anyone has a better option. Yeah, I'd be glad to hear them. Okay, so that was all I have. So yeah, I'm happy to discuss the problem further and possible solutions.
All right, thank you. Taki, go ahead, you were first.
Thanks. Yeah, first of all, thank you for doing this work, and wow, what a mess. So I like the DHCP-T type proposal off the top of my head, mostly because it kills the concept of TOS entirely. Because as you have, as Dave is also saying in the chat, and as you have demonstrated here, conflating them into one byte and one field is really actively harmful. And these bugs, like especially the ECN routing bugs, are really annoying to, like I've seen those in the wild, and oh my goodness, it's incredibly difficult to troubleshoot. So I am all in favor of doing something like this and just getting rid of, like, always mask out these ECN bits, treat DHCP as something completely separate from ECN, and just clean up everything. And I think like that goes for V6 as well. Like I very much doubt that anyone is actively relying on actually routing on these ECN bits, because that just breaks things.
Yeah. So I agree. I'd really like to clear the ECN bits every time for IPv4 and IPv6. That would make things much more consistent. Yeah, I'm just always wary of unintended side effects, and I've seen very weird setups into the wild in my previous at my previous employer, which was a small ISP. So now I don't really make. I try to not make any assumptions about how people use the fields or how they use protocols, because people are really very creative. So that's why I was a bit prudent about masking the ECN. But if the consensus is masking the ECN bits, even for IPv6, I'm all for it.
So I would think that if someone, so your concern is also, is someone using this actually as for policy routing, right? Like through IP. So my thought would be that if that really turns out to be something people want, that should be a separate field that you can like explicitly tell IP that you want to use the ECN bits, but it's not just part of the task byte. It will then be DHCP this, ECN this, and that will go into the routing table.
Yeah, that's a possibility. But I would be very surprised if people use the ECN bits for routing on purpose. I'm more wary of administrators who would have just try to do policy routing using the TOS. And they want to use one TOS, they start with one, and they don't realize it's the ECN bit. So with IPv6, you can do this on Linux, and without even realizing you're breaking ECN.
Right, yeah. I think so. In any case, we can clean up the code in the kernel, right, with something like this. And then at some point in the future, if we do dare to flip the default behavior in IP, that could be sort of a separate thing. I see your point in that there will probably be someone whose use case is using this, but yeah, I don't know. ECN is also like Linux boxes by default will speak ECN if spoken to, right? So people would almost have to go out of their way to, I don't know. I would be surprised if this is in the wild, but maybe I'm just optimistic.
Yeah. On the other hand, it's not possible with IPv4. So yeah, maybe it's really unlikely that someone did this for IPv6.
They would have to actually deploy IPv6 in the first place, which
yeah. They would have to deploy IPv6 in the first place and have a different way of doing policy routing in IPv4 and IPv6, because this kind of trick wouldn't work for IPv4. So yeah, maybe it's safe to just clear the IPv6, the ECN bits in IPv6. Also, do you have any comment about allowing the high order DSCP bits in IPv4? Is it something that you guys would consider safe or not?
Off the top of my head, I don't see why not, but just for consistency's sake, and also like the RFCs are pretty clear that it's defined identically, right? For like 20 years.
Okay, so I'll weigh in here. This is Dave Taylor. Can you go to the conclusion slide? I'm going to +1 a lot of the discussion you guys are just having. So To answer your last question, I'll go in reverse order. Yes, please allow the higher bits in IPv4, make the behavior the same. Having the same behavior between IPv4 and IPv6 is a good thing, especially as we want people to transition from IPv4 to IPv6 and not have to change fewer things in their policy and to change fewer things in their heads and training and so on is a good thing. So we really want the same behavior. So, and what you get in an ideal world, absolutely full DSCP support for IPv4. Yes, please use the higher bits too. Absolutely, please same behavior for IPv4 and IPv6. I might quibble with the wording on the second bullet. TOS shouldn't break ECN. In an ideal world, we would get rid of the concept of TOS altogether. And there's really two different fields, right? There's the DSCP field and the ECN field. And anybody that's talking about TOS per se, in an ideal world, that concept would just go away. Okay. Now, I'm talking about the ideal world, not what you can realistically do, but in the ideal world, there would be no such thing as TOS. We wouldn't use that term. That wouldn't appear in any APIs. And of course, yes, and I want a pony. Okay. What we can realistically do, I would, yes, absolutely mask the ECN bits from anything that's using TOS now, and just have anything that's using TOS right now use the DSCP bits, all of them, right? All 6 of them or whatever it is. If somebody really has to do something because they have some weird middle box that needs some other behavior and it needs to route on ECN, gosh, I hope nobody ever does that for the reasons previously mentioned. But if they did, then you could say, well, okay, you could always do something like have an override by installing an eBPF program, right? You can have a program that can muck with the fields and put whatever you want there. So you have another out no matter what, but we want to incent people to do the right thing. I would say as far as APIs and things go, having exposing DSCP and ECN as separate fields or separate APIs, separate macros and stuff is a good thing, right? Get people to build their right code as they're at least porting code or writing new code or whatever. You talk about, removing uses of bad macros. You never know what somebody else is going to do, but if you make the right macros and incent them to use that, you can deprecate APIs, you can deprecate macros, you can remove them, whatever makes sense to do in a staged effort. You'd mentioned that there might be some admins out there that have policy that might be relying on bugs. Well, that's true for just about any bug that you want to fix, right? There might be somebody that has policy or configuration that tends to be relying on that even when they shouldn't. So I wouldn't stop that from trying to push patches and things. You might want, if you have to, some configuration knob that you can revert to previous behavior if that becomes an issue. I don't know whether it's an issue, but otherwise, yeah, please incent people to do the right thing. And I think that's saying, option 1 is something that's in that category because it treats DSCP and ECN as completely separate fields. There's never any such thing as an 8-bit field, right? There might be an 8-bit value that holds a 5-bit or 6-bit or 2-bit or whatever field or whatever, but there's no such thing as an 8-bit field that you're treating as actually 8 bits or any other combination that combines both DSCP and ECN. So that's my take on it. Thanks.
So yeah, thank you. Yeah, I absolutely agree with everything you said. Just to reiterate, one point I made to Key is that yeah, I don't want to break existing setups, and yeah, that's really the reason why I was so cautious when changing the behavior. Yeah, and following what you said, if I come back to all these IP routes and IP rules, you would consider all of these examples to be bugs. Yeah, just to be
and in your IPv6 case, I would consider the IPv6 behavior that showed to also be a bug.
Yeah.
So yes, I agree. That's why those are excellent examples, right? I would consider all of those to be evidence of bugs, right?
Mm-hmm. Okay. If we really can consider that the DSCP plus ECN is the only valid interpretation in the Linux kernel, this really simplifies the problem.
Yeah, so this notion that says, the TOS parameter is ignored for IPv6, that's great. In the ideal world, there's no such thing as a TOS parameter. There's a DSCP parameter and there's a ECN parameter, but there's no such thing as a toss parameter, right? Trying to configure a toss parameter would be an error because the command to configure toss is deprecated or not even present in IPv6. That would be the ideal world, right? You have to configure your rules and stuff based on DSCP or whatever. The toss as a label does not even exist for anything in IPv6. So just like it doesn't exist in any RFC right now, it's just an artificial construct that exists in a command right now for IPv6.
Yeah, I agree, but I would go even a bit further. So IP route, in my opinion, shouldn't have neither a TOS nor a DSCP parameter. If we want to route packets based on the TOS or DSCP, that should be done with IP rule. So for me, it makes perfect sense to not have neither TOS nor DSCP parameter to IP route and leave this task to IP rule. And I believe that's the reason why that was never implemented in IP route, actually.
All right. As Jonathan was reminding in the chat, there will be a closing keynote in a different track, right, at 11 a.m. in 5 minutes. So just wanted to remind people. If anyone has any other questions, we still have 4 minutes to go. Assuming not.
Last summary is I don't think you're hearing any support for option 2. Everybody likes option number 1 from people that have an opinion here. So hopefully that gives you a feedback that's useful.
Yeah. That's really the kind of feedback I was looking for. So yeah, that's great.
I'll add that I'm happy to review patches if you send them.
Mm-hmm. Yeah, I'll work on it.
All right, folks, then. Thank you very much for the talk. This concludes the BPF and networking track for today and the LPC conference for the BPF and networking track together. So, yeah, time's up for this. And I hope we'll see each other next year in person. Thank you very much for contributing both talks and discussions and questions. And yes, please do consider joining the closing keynote session. Bye.
you.